Record. Test. We don't have another set of headphones, do we? I'll get some today. I won't be able to connect. All right, this is fun. We'll just hold it like 3 or 4 away from the tablet. Okay. Did I hit record? Okay. Let's see. Okay, hopefully that's visible. It doesn't look like it is.
There's a slight background echo.
Okay. Okay, we can see now. All right. So, turn down your volume a little bit. What am I getting noises from? All right, so we're doing topology. So some of you probably haven't seen any topology before, or probably haven't even heard of it. So what exactly is it that we're trying to do here? So in calculus, you've probably seen a lot is made of continuous functions. Many of the central theorems that you'll cover in Calc 1 say will deal with continuous functions mapping from the real numbers to the real numbers, or say from some closed bounded interval. So what that states is essentially that if you've got a function on some, we'll say 0 to 1, some closed bounded interval, and it maps to the real numbers and it's continuous, then you get essentially visually, you can think of this bottom axis on a graph being an interval between 0 and 1, and this upper axis, you can call this x, and then we'd call this up here f of x. And your continuous function will look something in effect like this. And so you can take f of 1 and f of 0, and all the values in between these two on the y-axis here, so to speak, will be reached at some point along this interval, in the sense that we can look somewhere in this interval and find a point at which the function maps to the value that you pick out from the y-axis. So if I were to pick this and then draw a line across, you can find somewhere where it intersects the graph. So there's 2 or 3 of these. There's things like mean value theorem and so on in calculus. But we can take the idea that you study these functions on the real numbers and study them in a more general setting. And that's what topology is about, essentially. So we're taking the idea of continuity and studying continuous functions on different spaces from the real numbers. Let's see. So for instance, we could look at, say, some kind of sphere or something and study functions that map from the sphere down to the real numbers. Or you could study functions from a sphere to a torus. or just anything in general. And we'll have related theorems to these. There's two ways we could go with this. So one is just going down the route of like point set topology and just studying topology for its own sake. The direction I'm going to go is kind of different. We're going to study topology with an eye towards algebraic topology. And the idea here is that we take these spaces like spheres, tori, the real numbers, just other sets in general, and we try to figure out different equivalence classes of these spaces, which have certain properties. So you can build up these what are called gadgets or functors on these spaces, and under certain operations, topological operations, these functors do not change. So, for instance, we'll compute some things like, say, for the sphere, for instance, we'll be able to compute like the fundamental group of this. So if I compute the fundamental group of this, and this is usually denoted S2, this would be equivalent essentially to just a set with one element or a group with one element. And then if I do any kind of continuous deformation of the space, say if I change this into like a cube, then it's going to preserve the fundamental group. So we're going to compute invariance under certain kinds of continuous maps. So essentially what we'll be doing is taking spaces and converting them into gadgets, which are invariant for certain kinds of operations. All right. Let's see. If I can get to my notes. Okay. All right. So who's in the voice call? Let me see. How do you even see it? Okay. All right. All right. So we need some definitions to begin with, so we can start to work towards algebraic topology. So firstly, the first definition I'll give is what is a topology, right? So I'm sure all of you guys are familiar with what sets are. So we'll leverage the notation from sets. So just let X be a set. So let X be any set. Then you guys are familiar with power sets. So if I speak of, say, P of X, then this would be the collection of all subsets of X. So Y such that Y is a subset of X. Or, for example, if I take, let's let X be A, B, C. So just three elements. What would the power set of this be?
A, B, C, A, B, B, C, A, C, and A, B, C in the empty set.
Right. Okay. So you've got A, B, C, the whole set. And then you've got A, B. So all the pairs. What did I miss? The singletons. Whoop. And then the empty set, or just this vacuous pair of braces. So that's the idea. You just take the collection of all the subsets. So then we say a collection, let's call it T, right, it's script T, which is a subset of the power set of X, is called a topology. On X. So you take sets, you can do this for any set. You take sets and you define structures or subsets of their power sets, which are called topologies, provided you have to satisfy 4 criteria. So the first criterion is that the empty set has to be in the topology. Second criterion is the whole set, X itself, has to be in the topology. And if you're not used to working with power sets, you may need to see this stated one time. So for example, the set we just were talking about, the, what was it, X equals ABC, the power set itself was a topology under these 2 criteria, because it contains, I'll just write out these 2 sets. It contains firstly the empty set, and then it also contains the whole set X, which was, of course, ABC. So the third criterion is that you have to be able to take any, so for any collection of subsets of X, we'll call them, say, U sub alpha, so an indexed family of sets or subsets of X in the topology, where alpha's in the index set J in the topology. We should have, whoop, the union over this index set is also in the topology. So essentially, you can take arbitrary unions and of sets in the topology, and you get another set in the topology when you do that. So arbitrary unions. And then the fourth criterion is similar. So the fourth is you should be able to take any finite collection of subsets, or more properly, if U and V are in the topology, then their intersection is in the topology as well. Okay, so this seems kind of abstract. The intuition for this is, firstly, we need to give a name to these sets in this topology. So sets in a topology are called open sets. Okay. Let's see. A couple of examples in the real numbers. Let's see. So when we're building up the topology on the real numbers, we start with the open intervals. So you can just, let's see. So the real numbers have a topology given by any open interval is open. But is this sufficient? This should not be sufficient because we can take an intersection, or actually a union. So if I took, for example, where's my pen going? There we go. If I took, for example, -1 to 0, and I union that together with 2, 3, then this is not an open interval because it looks, in effect, like this. So it's not an open interval itself. So it would not be one of what's called a basis or sub-basis element here. So the topology on R is not quite exactly obvious when you first see the definition of a topology. The way it's defined is using an additional definition here. So a basis, or actually properly a sub-basis, for a topology on a set X is a cover of X. So what I mean by that is, if I have a set X, say the real numbers, and I take all the open intervals on the real numbers, then I am able to cover the entire, like, so say if I take the set, we'll call it S, where S is just all the open intervals, so A, B, where A, B are in R, and A is less than B. And this forms a cover. So what I mean by that is I can union over all the elements in S, and this actually gives me R. So any element of R is contained in one of these elements of S, or sets in S. So to go from a sub-basis to the topology that it produces or generates, you take all of the finite intersections, or you take all the pairwise intersections you can. So the intersections of any two open set or open intervals in our sub-basis for the real numbers are just the open intervals again, because consider if the two are disjoint. When I take this interval, or when I take this intersection, if we suppose that B is less than C, then the intersection is just It's just the empty set. And if I suppose that, let's see, if A is less than C, is less than B, is less than D, then what this looks like is something to this effect. And this would be the intersection, so that's still an open interval. And then if one's contained in the other, then of course the interior one's the intersection that you get out. So already they're closed under this subbasis, or in fact this basis is closed under intersections. But then furthermore, after you take the intersections, you take all the arbitrary unions, and that gives you the topology. Because necessarily, let's see. You have to check that it satisfies these criteria. So you can take the intersection of two disjoint sets in a subbasis, and you get the empty set. And then since the subbasis forms a cover of X, you can take the unions over all the elements, and you get the whole thing, the whole set. And then because you generated the topology precisely to achieve this, you have closure under arbitrary unions and finite intersections. So that's just automatic. There's a criterion to qualify for being a basis for a topology, but I won't give that. It's sufficient for our purposes. Just think of a basis as having been generated by some subbasis, just taking intersections. Okay, let's see. Let's see if I missed anything before I go on. Okay, so a couple of more definitions. So open sets are properly the elements of the topology. Okay. Then closed sets are the complements of open sets. So this agrees with the usual notion of closed set that you have for real numbers. So the way we do this is, let's say I want a closed bounded interval in the reals from A to B. Now what I can do is, to see that this is a closed set, I can look at the topology that we've generated on the real numbers. And I can look at, let's see, the union of two. Let's actually do it this way. So to start with, I'm going to write this out as a number line. And we want to only include numbers in this interval. So here's A, here's B. Now there's an open set, or an open interval properly, that is like this. And then I can also take a union of this one, which goes out to here, and then union that with one which goes out further, and then in fact take the union of all the open sets, or all the open intervals that have right sides equaling A. So we can make the set big A be X to A open interval such that X is less than A. and then just take the union over the set A, and we get precisely the open set negative infinity to A. So this is an open set because we can take arbitrary unions. And then do the same thing for the other side, where you just pick out B, X, where of course B is less than X. And then the union of B is B to infinity. And then when you union these two together, you get the real numbers less, well, closed set AB. And of course, this is just equal to the complement of AB. So closed intervals are the complements of open, or closed sets are the complements of open sets. They are characterized kind of backwards from how the topology is. You could actually define topologies in terms of closed sets just by swapping the cardinality in these two criteria. So you would have arbitrary intersections of closed sets and finite unions of them instead of the other way around. Okay, that's closed sets. Let's see, what else do we need? Okay. I think that's enough for right now. I'm working up to an example that I want to do. So I talked earlier about topology being really about continuous maps. So we can define continuity in terms of this kind of construction that we've made now. So a continuous function. In fact, I need one more thing. So a topological space is any set X, or any pair X and T defined on X, where X is a set and T sub X is a topology on X. So when we endow a set with a topology, it becomes a topological space. Sometimes I'll just say X instead of saying this pair, because it's a little bit to write out. Another way we might visually describe topologies is, say, if I've got a set ABC, I might draw the elements of it as points. And then, of course, it has to have the empty set and the whole set as open sets. So I'll draw open sets as like circles around the elements. And then this would be a topology because it satisfies the criteria and the four criteria. You could define some others, like, for instance, if you were to add this, that would work. This would not be a topology because when I take a union of, if I label these A, B, and C, then this is an open set, and this is an open set, but this is not an open set. So you see that this is just a subbasis, or in fact, the basis for a topology. But if I complete it by taking unions of all the open sets, then I get a topology. So that visual may help to solidify this a little bit. But that's sufficient. Let's see. Okay, so if I've got two topological spaces, say X with a topology on X and Y with a topology on Y, these can be any sets endowed with topologies, anything at all, doesn't matter. X could be something like the real numbers, and Y could be something like just that ABC set, or it could be an empty set, it doesn't matter. We can take any function which maps from X to Y and say that it's continuous under the following criterion. Let's see. If so take any open set U in the topology on Y, and then check the inverse of F, which is precisely on U, which is defined as, of course, X in X, such that F of X, why did that make that bigger? Is in U. Is open in X. That is, F inverse of U is in the topology on X. So really what this is saying is anytime I have a function going from X to Y, two topological spaces, if I can invert the function and this becomes a diagram going in this direction on sets, then F is continuous, if that makes sense. So let's see. Yeah, so if I've got two blobs, say two sets like this, and this is X, and F maps that way over to Y, then I should be able to take any open set and then look at, call that U, and then look at all the things that map by F over there. If the pre-image, no matter what open set I chose in Y, is open in X, then F is continuous. Right. So this is kind of like my favorite sort of characterization of this. Because it's nice. You can take diagrams and sort of flip them backwards and just write topologies instead of the original sets that you were working on. So this agrees with the definition of continuity that you probably covered in calculus, which is formulated in terms of epsilons and deltas. We can check a couple of examples real quick. So let's see. If I take, for instance, F from the reals to the reals, defined by X maps to X squared. Of course, this is continuous. Let's see. Yeah, you could just visualize the graph. And then any open set I take on the y-axis here, or the f of x-axis. You can look at how it projects onto the function. So just kind of draw this like box going out in both directions forever. And then you'll see that you can project down where it agrees with the function, or where the function intersects that box. And you'll get open sets here. And there's really only like 3 cases. So you could pick an open set down here, and that wouldn't intersect with the graph anywhere. So you would get the empty set, which is of course open in the real numbers. You could pick one up here like we've done, and you'll get the disjoint union of 2 separate open intervals. Or you could pick something like this, where you'll get, it will agree on this half closed interval on the f of x axis, but when you project it down onto the x-axis, you will get, let's see, this sort of behavior. So you'll get this open interval from here to here. So those are really the only 3 cases. So this one's continuous. Okay. All right. So this generalizes a little bit further than the epsilon delta formulation of continuity, because you can take things like, say, if I took f defined on, let's see, what do you guys think of when you're like looking for a discontinuous function? What's probably like the most readily available thing? We could use like the step function or something. Hmm. I'm trying to think of kind of like a tricky one. I guess we can just do with like some kind of gap first. So if I took some linear graph, and then I took, let's see, make these closed at these points, and then make it obviously discontinuous. And then you can check that it is discontinuous by taking something like this region, projecting it over here. And then you'll see that it agrees here. So this is actually closed. Or sorry, that's open. My bad. The other side's closed. Like so. So we took an open set in the codomain, or the target, and then saw that it maps back through the inverse of the function to a non-open set here, because this side's closed. Okay. Let's see. But there's some tricky cases. It really matters rather deeply what you define your source space to be. Let's see. Also, I didn't see the questions yet. Let me go back through. So referring to the topology taught, does the definition of open and closed set imply that open sets are mostly used to constrain and define closed sets? Let's see. I'm not sure what you mean by constrain and define.
When you were initially explaining it, you basically just said, yeah, an open set is like from any point to here. And then your
Right.
definition of closed set was, yeah, anything not in the open sets.
Oh, okay. So it's not properly anything not in the open sets. So we can actually
Between
define
the open
something that's
sets.
neither open nor closed, right? So one way to do that is for instance, you can take on the real number line, you can take something that is half closed, half open. And when I say half closed and half open, I'm kind of abusing terminology. I probably shouldn't do that, because when you speak of open intervals and closed intervals, that agrees with my definition of open and closed. But this, when I say half open and half closed, there's really nothing topologically open or closed whatsoever about this, except locally, per se. So the problem with this is, this is clearly like, let's see. If I took, for instance, 0 to 1 closed on the right-hand side, I could say that this is the intersection of, let's do this. Actually, it's easier if I change the numbers a little bit. So this way. So this would be the intersection. And k equals, say, 1 to infinity of -1 to 1 over k. Right, because no matter what k is, it's always positive. So you always have this is the subset of whatever this is, depending on k. And then 0 is always in here. But if you pick out some epsilon greater than 0, then you can find some k greater than 1 over epsilon. And then when you do that, you just like flip the inequality here. That gives you 1 over k is less than 1 over epsilon, or excuse me, epsilon. So when you do -1 to, you ask if epsilon is in -1 to 1 over k. It won't be, because epsilon's greater than 1 over k, so it wouldn't be in there. So no matter how small you make epsilon, there's some open set that you're intersecting with in this intersection that will not contain it. So you can see this is an intersection of infinitely many open sets, but there's no way to construct it using open sets, given like the topology that we built up. You can define another topology this way, but the usual topology on R that we've used, with basis being the open intervals, won't have this as an open set in it. And it won't be closed either. So the way to see these is actually there's a separate definition of open and closed set. So open can actually be given as every point. So if U is open, it's in the topology on X. Then for all U, little u in U, so every point in U, so say I've got some kind of blob set and then an open set in that blob, you can pick out any point you want. And no matter which point you pick out, there will exist another open set V, say this one. Let's see. So that U is an element of V, and V is a, let's see, just a subset of U. And then for closed sets, so basically what this is saying is every an open set contains a neighborhood of each of its points. So this one would not be open, right? Because if you look at 0 and 1, well, 1 is in this. So we should, if this set were open, we should be able to find some kind of open neighborhood of 1 that is contained in this set. So it should be A to B, some open interval, such that A is less than 1 is less than B, and A to B is contained within 0 to 1. But you see that this isn't the case because B has to be strictly greater than 1. So it can't be inside of it. And on the number line, this makes sense too, right? You can just draw it. And it looks like this. You pick out 1 right here, make a small interval around it. You see that it can't be fully contained within that set. So it lies on the boundary. And then the alternative definition for closed sets is you need something called limit points for that. So firstly, limit points are let X be a topological space. I'll just abbreviate that. Let E be any subset of X. It doesn't have to be an open set or a closed set or anything. A point X in X is a limit point of E if every open neighborhood of X intersects E minus X. So the idea is this. If you've got X, your overarching space, and then you pick out some set E, who knows, maybe it'll contain parts of its boundary, maybe it won't. Maybe it'll have some part jutting out that's like one-dimensional. Maybe it'll have some disparate points elsewhere. But we check if a point is a limit point by firstly singling out that point, and then seeing if we can draw an open neighborhood around that point that doesn't intersect E. So this would not be a limit point because we can find some open set that contains it and doesn't intersect E. So this would be X, this set would be E. This, however, well, even if I draw it really close, I can still draw a tiny open neighborhood around it, so it won't be a limit point. But anything, say here, even if it's not contained within E, it still doesn't matter. I can't draw any open set around it that doesn't intersect E in some fashion. So if E is this interior or this region here, then clearly it kind of touches any neighborhood around this blue point. So this would be a limit point of E. One kind of interesting example is that if we were to let X be the real numbers, E be the rational numbers, so all the fractions essentially of integers, square root of 2 would be a limit point of E. Let's see. And the way to see this is you can, let's see, say square root of 2 is here, and then you draw any open interval around it, no matter how small you pick it to be. And then this is going to contain some rational numbers in it, because the rational numbers are dense in the real numbers. No matter how small of a space you pick out around the square root of 2, there's going to be some rational number in that space. In fact, infinitely many of them. So, in fact, the real numbers are actually said to be a limit point completion of the rational numbers, because the rational numbers themselves have no limit points. Or, yeah, you have to take the real numbers to obtain that. Let's see. Actually, that's wrong. The rational numbers, every element of the rational numbers should be a limit point. All right. Because you take, yeah, in the subspace topology it should be. Okay, so the idea of a closed set then under the restatement is a closed set contains all of its limit points. So the set we were talking about, 0 to 1, half closed, half open, is actually not closed either, because 0 is a limit point of the set and it doesn't contain it. So necessarily it's not closed. There's a proof that these conditions are equivalent to the earlier stated definitions, where the open set is just any set in the topology, and then the closed sets are the complements of the open sets. So this isn't synthetic. We're not just coming up with this additional definition. But it suffices to say that sets are not necessarily either closed or either open. Like, it can be neither. And then you can also have clopen sets. So for instance, the empty set in any topology is actually the complement of the whole set. So you see that the whole set must be open, because any topology must contain both the empty and the open sets, empty and the whole sets. But since you can take the complement and get another closed set of each, that is not accepted terminology, by the way. Don't use that. But yeah, both the empty set and the whole set are both closed and open. So, but don't call it what he just did, please. All right. So let's see. And yeah, basis is being used in the usual sense. You may be thinking of it in terms of linear algebra. It's not exactly the same. Let's see, why the drawing you were doing showed that function is discontinuous. Okay. So we had that function that had some jump discontinuity in it. And I was just taking it to be a function. Let's do the one you suggested, the indicator function. Or not the indicator. What was it? Was it the indicator? Okay, let's do step then. So we'll have it open here, So there's a open circle, and then here there's a closed circle. So this one's not open because, well, firstly we need to define what the domain and codomain of this function are. So this is x, this is f of x, and then we have f is a function from reals to reals. So this one is discontinuous because, well, what's the definition again? We can take in order for it to be continuous, we must be able to take any open set in the codomain here and map it back. So let U be a open set in the real numbers. And in order for f to be continuous, this must imply that the inverse of U under f, or the preimage of U under f, must be open in R as well. So I should be able to, in order to show this is discontinuous, I should be able to show that some function or some open set maps back through the inverse to some non-open set. So how might I do that? Well, one way I can do it is I can pick out just this, right, in the codomain, and then, you know, if I draw out this bounding region, let's try the one you suggested. The -2, so this is 1 properly, and this is 0 on the y-axis. So you've said -2 to 2, so let's try that. Well, if I draw out this bounding region, you'll see that it contains everything, right? Yeah, so that's problematic, because what we get is, if I let, well, let's just do it explicitly. So -2 to 2, this actually would be the entirety of the real numbers. And that's open. But if we're a little more careful and we make our open set a little smaller, more specific, doesn't matter how small I'll make it, actually, it just needs to be around just this point, not the other one. Then I take the preimage of everything that this projects onto, or isn't contained in this bounding region. You'll see that it's actually this set, and it goes on forever in that direction. And the reason this isn't open is because 0 is in the set, and nothing below 0 is. So there's no open neighborhood of 0 contained in the set. So since it contains a point for which there's no neighborhood contained in the set, it can't be open. Yep. So you get, when you do this, I don't know what just happened. There we go. When you do this, you get f inverse of, what is it? 1/2 to 3/2. You get 0 to infinity. Yep. Okay. Let me check something. So I want to give a trickier example of a continuous function. Valeria, do you remember the functions that this gave us? Checking continuity. I can't remember what it was. You have to restrict the domain in some way. It was with isolated points. And they didn't look continuous, but they were, right? Remember that? I don't remember what it was. Let me see if I can construct it real quick. There's a bunch of us in the same room together. That's who. Let's see. There's a nice example that I can't think of. If I had Rudin on me, I'd probably look it up, but okay, let's try it. So I want a function that maps into the real numbers, But I don't know quite just yet what I want it to properly be. I think I know what I want it to be now, actually. I'm going to leave a little space there to change something. And I want you to tell me if this is a continuous function or not, according to what you're used to. Anyway. So say I've got a hole right here. Would this be a continuous function? All right, I got 2 answers so far. Any more? Okay. Your phone? It's in the off-topic room. Okay. You say it's a discontinuity. All right. Okay. So jet printer is correct. I didn't properly define the domain. But there's something a little strange here. We could say, you know, maybe this is defined in the way you'd see in like a college algebra class, where it's something like, you know, I start with 2x as my graph, and then I want to remove a point. So what I say is like, okay, let's multiply this with, what is that? X equals 1 roughly. So we can do x minus 1 over x minus 1. And then, you know, I can, to make it look nice, I can just like multiply the numerators together, and I get what? 2x squared minus 2x over x minus 1. And that would give you this graph. And then the class would have you like answer whether it's continuous or whatever. And 5-ho is correct. Like you would put for your answer removable discontinuity. The trouble is this isn't a discontinuity at all, and your class was lying to you. It just doesn't make any sense to call this a discontinuity. It looks like it sure when you draw the graph, but the graph's this kind of just intuitive object. Like it's not really in line with what the function itself is, or the space underlying this. Yeah, it's going to be continuous. We can actually check this. So you have to remove this point 1 from the domain to be able to say this is a function, because a function has to be defined everywhere on its domain, right? So I should be able to take anything in this, say, if I didn't write this, I should be able to say 1 maps to something in the real numbers. But it doesn't, so it's not a function. So I need to remove that from the domain. Now when I do this, it turns out that let's look at all the qualitatively different open sets in the codomain here that I could kind of project back through the pre-image of F. So there's one that contains the point, right? That one will have here will be open, here will be open, and then here it'll also be missing. So this is actually open. Because it's a union of 2 open sets. Right, so it's that one and then that one as well. You union them together, and then it's open. And then also we could have taken something that comes right here, goes here, well, you'll just get the left-hand side of that. Or if I had done it here and up here, I would have gotten the right-hand side. Or if I did something outside, I would have gotten just like some kind of smooth, you know, like this. It wouldn't be missing that point. So this turns out to be a continuous function. On the other hand, if I had had something like this, remove a point, stick it up here, have this be a function from the real numbers, then I can take a interval in the codomain here, project it back onto the domain, and you get everything over here, which looks open, but then you've got that union with this singular point, which is, well, it doesn't, the set, which is union, that does not contain an open neighborhood of this point, so it can't be open. All right, that's enough of that. So some more definitions. So we can obtain a lot of topologies that are kind of interesting really quickly with this next definition. So this allows us to start with some set, have a topology on that set. So we have the topological space that we're starting with. So let X be a topological space. Then a subset Y of X, and it can be equal to it, and it works still, but it's kind of useless to talk about that. So just assume I mean a strict subset, like something actually smaller. So a subset of that topological space, and recall that I'm not talking about the Y doesn't have a topology yet, it's just a set. Can be given a subspace topology as follows. All right, so we need to establish a criterion on subsets of Y, this so-called subspace, so that we can say whether that subset of Y is open in the subspace topology or not. So the way we do this is let U be a subset of Y. U is open in Y, not in X, because recall that since it's a subset, you've got this set up, right? So you got this, it being a subset of Y, so naturally it's also by transitivity a subset of X, so you could consider whether it's an open set in X. But it doesn't even have to be open in X to be open in Y. It just has to satisfy this. So if and only if U intersected with Y is open in X. Okay. So an example of this, we can draw this in the plane, right? So you can take a plane, the real numbers, squared, right, R2. Imagine this goes on in both directions forever. And I can take any subset of it. So let's take some small piece here and call this Y. And call this one out here X. Clearly Y is a subset of X. Well, let's see. If I take a set like this, actually, I forgot to say the open sets in R2, the plane, are the circles that don't contain their boundaries. So those are the basis elements. So you can take unions of them. So like you can patch together little circles. And then if you wanted to get a square without boundary to be an open set, all you have to do is like draw out the, like kind of make a stencil in some sense of a square. And this won't actually be the open set yet. But what you do is you take the collection of each point in the square in the interior, not on the boundary, and you can draw a small circle around it. And then once you've done this for all the points in the square on the inside, you can union over these little circles and you get the interior of the square. So it doesn't actually contain the boundary. So any kind of shape you want is open set in R2 as long as it doesn't contain its boundary. And it contains like a circle inside around each point, right? Right, so this is open in X, and the nice thing about this is if I let this be U, then U intersected with Y is already open in X. So it's an element of the topology on X. So this would be open in Y as well, because it satisfies the criterion for the subspace topology on Y. But kind of interesting example is, let's see. If I take something like this, let's see. This should not be if and only if, by the way. It should just be one if. And then I contain this boundary right here. Actually, let's do it this way. Let's just make it obviously open in X. This is open in X. So when we restrict this to being a subset of Y by lopping out all the elements outside the square, it turns out this stops being an open set in X because on the boundary there's no point, or all the points on the boundary have no open neighborhood fully contained within the open set E, or U, this red set. But since this is, let's see, I think this definition is wrong. So it's open in Y if there's two ways you can define this. So actually you can just pick out any subset of X that's open. So then U intersected with Y is open in Y, or is an element of the topology on Y. Okay. So yeah, it turns out that this set is not open in X, but since there's some set which is open in X and which intersects with Y to give me this red set is open in Y. Right. Okay. So this is called the subspace topology on Y. Now, this is rather nice because we can get, say, a topology on the rational numbers this way. So we say Q inherits a topology from R. And you can look at continuous functions between, like, from Q to Q, right? So anytime you have a topology defined on a set, you can suddenly study. Okay. All right. Let's see. What was the next thing? All right. Okay, so now there's a question that's a little bit stronger than being for function. So let f from a space X to a space Y. These are topological spaces. Then if you've got, let's see, if f is bijective, the root f to be bijective is I want not to be. I'm gonna so I get that f is actually from the topological y to the topological, or to the from the topological. But I don't. In general, if f is checked, this actually is not. Let's see. How should I say it? It's not a single act. If we were to look at f inverse on y and plug in individual points in y to f inverse, so like x here, and then y here, and f here. A, for instance, maybe this here maps to this point in y, and this point on here also maps to, call this low. signal's bad. Why is it slack? We can try mine. Yeah. Is it working any better? No. That's not right. Let me just switch networks. Here. SSID, please, if you see that. No. Okay. Working now? There it goes. Right. You're still a ways behind me, so it's flashing in and out of your screen. We're good now? All right. So you should be able to see what I'm drawing now. Scribbling. Okay, good. All right. All right, should we good? Yep, good. Okay. Sorry about that. All right, I'm gonna try to wrap up the. I don't. Is it? What is going on? No, maybe. Is it? It's like 10 seconds behind, though, at least. It's totally frozen in that frame. Wow. That's what I need to work, though. I'm not in any. I don't have any installed on here. Do I hear something wrong? I'm gonna like. Yeah, I know what to do. Let me go on airplane mode for a second. That usually works. Okay. That's crazy. It's still not working. Are you guys, so on our side, we're streaming to another laptop, and it looks like the screen's like flashing black every few seconds. Is it doing? Go out and back in. I'm moving my screen and yours doesn't move at all. It's been stuck on one frame. There it goes. Okay. Hopefully it works. Okay. So yeah, so homeomorphisms. Hopefully you guys can see everything. I can't see what you can see. So just ping me if I lose anything. Or if I lose connection again. So yeah, the comments from Brandon are correct, it seems like. So if you've got an injective function or a one-to-one function, then you can always take the inverse, right? So if f, this is the notation we use for it, is injective into y, has a little hook arrow, then you can always take f inverse, and that will give you a function from f of x to x. The trouble is you don't get a function from y to x, right? Because there may be, you don't have surjectivity by default. You haven't assumed that you have surjectivity. You only have injectivity. So you may not have anything in the image of f that like coincides with certain elements of y. So you have to make sure that you just take the restricted codomain version of f. We'll call that, say, f prime or something, which is a map, which is injection, or sorry, a bijection. I'll actually write that this way. To y, or sorry, to f of x. But yeah, in general, you don't have the ability to just flip this arrow unless you have a bijection. Yeah, so the hook on the arrow means injective. So it means anytime you have FA equals FB, that means that A equals B back in X, right? Yeah. Yeah, that's right. 1-to-1. Yeah, and that's what Nick just said is if I had written this to arrow, the double-headed arrow, that would mean surjective or onto. So I guess you could write a bijection this way if you wanted to, just including both of those symbols. So yeah, I'm gonna go ahead and require that f be bijective for this definition. So I'm going to establish 3 criteria for this. So f is bijective. F is also continuous. You know what that means. And also, f inverse as a function from the topological space y to this topological space x, happening also to be a bijection, is also continuous. then we say F is a homeomorphism. Now, some people have an easy way to remember what a homeomorphism is in terms of a mnemonic or another term used for it, which is a F is a bicontinuous function. I remember reading Munkers and thinking that this helped me memorize these criteria a little better. All right. So when we say homeomorphism, what we're saying is, okay, F is bijective. So it's a isomorphism in some sense. Its inverse is a function from y to x, and both of these are continuous. So what that means is, for all open sets U in Y, or in the topology on Y per se, the inverse of U is in the topology on X, and then also for all U in the topology on X, the inverse of the inverse of U, which is equal to just, because F is a bijection, you can do this, is also open in Y. So we say that F is an open map. So it maps open sets to open sets, and it's continuous, so its inverse is an open map. Oh, what just happened? I see, okay. So some examples. Hang on just a second. One sec. All right, sorry. So let's see. Yes. So examples. The real numbers are homeomorphic. We say that two spaces x and y are homeomorphic if there exists some homeomorphism between them, right? And of course, given the definition we've made, any homeomorphism going from x to y admits its inverse as another homeomorphism. So let R have the usual topology. And I'm going to use this symbol to denote homeomorphic. So this topological space is homeomorphic to any open interval in the subspace topology on R. So how can we show this? Firstly, we need to come up with some continuous map, which is F from R to AB, or we can go in the other direction, probably a little bit easier. And let's do this from -1 to +1. All right. So yeah, we are. Sorry, like we had the technical difficulties. Trying to get those ironed out. So somebody help me try to build a continuous function from the real numbers to this open interval. Just any. Using what you usually think of as continuous functions. You don't have to use the definition that we've constructed because it's equivalent to that. And by that, I mean the way you're used to doing it in terms of graphs and checking if there's like jumps in them or anything. No ideas? We can do it pictorially if you want. I'll actually go the other way. So a graph of this might look like on your horizontal axis, you've got an open interval. This is -1, this is 1. And here along the vertical axis, you've got this line, which corresponds to the real numbers. If I can figure out how to move it. All right, let's see. Did not mean to make that red. Okay. So we just want this to be continuous. So I can just, set 0 to be sent to 0 automatically. And then I want this to be continuous, so I have to start branching out in some way. And I want it to be a bijection, so I need to make it pass both the horizontal and vertical line tests. So I can just do something to this effect and some kind of asymptotic curve. Now, how would I represent this algebraically? You may know this is the tangent function, or a small slice of it. You couldn't use x cubed because x cubed is not asymptotic, right? So you need to use tangent or something like it. You could also use a sigmoid. Let's see. You could use hyperbolic tangent. Whatever you want. But as long as you can draw such a thing, you know that these two spaces are homeomorphic, right? Because this is both injective and surjective. And it's continuous. And we just, to check that it's bicontinuous, or that its inverse is also continuous, you can just flip it to get the inverse of it. So the codomain swaps with the domain. And then you flip over the y equals x line on the diagonal. And so this becomes, let's see. Like this. And of course it retains its continuity. You can see very straightforward. So this would be F inverse. Okay. So it turns out that I could have picked any open interval and we would see that the real numbers are actually homeomorphic to any open interval, because there exists a homeomorphism between them, which is represented by this graph. Now, another example. We can do, let's see. We can do some higher dimensional objects, such as a donut and a coffee cup. So by donut, I mean a torus. And we'll do, I'm not a great artist. Huh? What? You can, you want to draw? Well, yeah, so the way to see this is homeomorphic is you would have to take some kind of parameterization of this space, and continuously deform it into the other one numerically. It's kind of tedious to construct the coffee cup, so I'm not going to construct such a thing, but these two spaces are homeomorphic. And the usual way to do the homeomorphism is to turn the donut sideways, right? And then take this piece here, have the rest of the donut become the handle, have this piece expand out, and so you end up with this kind of shape. Let's see, you'll have some kind of like extruded rectangle or something. Or yeah, it's actually hollow. And then here you'll still have the handle. And then you can go from here to rounding out the cup part. Still have the handle sticking out there. And then take where you would usually drink from, and kind of just like continuously push it down into sort of like this well, and then go all the way down as far as you want, and you end up with a coffee cup. And it turns out that this is continuous, it's a bijection, and you can follow it backwards to get another continuous bijection. And so this is a homeomorphism. Right. Now, some interesting properties that we can start talking about once we have, let's see, actually, let's do one more example. This is actually an exercise for you guys. Take a point, and this kind of falls in with linear algebra. So take a point, say R0, right, the zero-dimensional vector space over R, and then ask, is this homeomorphic to a line, R1? Can we construct a homeomorphism between these two spaces? Is it possible? Firstly, can you construct some kind of continuous deformation of the real numbers into a point? Yeah, absolutely. So it's homeomorphism, by the way. Homomorphism is synonymous with a continuous map or a continuous function in topology. Homeomorphism is a bicontinuous function. Yep. Yeah, so bijective, continuous, and has a continuous inverse. Is there such a function between these two spaces? Why not? I need a rigorous proof of this. Why can it not be bijection? Yeah, I have full screen. You see where it says talks and all this stuff? There's a chat icon on that box. There, yep. Yeah, just leave that open. That's good. Okay. Also, I'm gonna move the chat to this. Like if you go to voice channels where the talk is, there's an open chat box, and I'll just post the picture that Brandon posted a second ago in there. That way YouTube will see what you guys are talking about. Yeah, so Strad suggests there is no bijection between these two spaces. So of course there isn't, because they have different cardinalities, right? There's only one point here, so there is no surjection in this direction. These two can't be homeomorphic. Now, a trickier problem, bless you, is whether these two spaces are homeomorphic. R2 and R1. Recall what the topology on R2 was. It's the unions of open balls or open circles are the elements of the topology, the open sets. Yeah, so I moved to the chat box for the talks voice channel. You can like see where it says voice channels and then hover over talks and then open chat. It's there. Like there's a little button. Yeah, so the question is now, you solved the problem of whether R0 and R1 are homeomorphic. The answer is they're not. The question is now whether R1 and R2 are homeomorphic. The trouble is you can't use the argument that there's no bijection between them anymore, right? Because they both have the same cardinality. They're both uncountable. Aleph 1 is their cardinality now. So either we need to find a homeomorphism or we need to determine that there does not exist one. Yep. So when you're stuck, just try constructing some things, right? So we know any linear map is continuous, right? We can try linear maps. But do we know that anything about the status of bijective linear maps, or the status of bijectivity for linear maps between R1 and R2? The trouble is you've got to have, if you want to squash this whole space down, well, what you need is essentially a matrix. What is it? Just, let's see. Not sure the actual function that is the bijection between R and R2. I've heard of, what was that, Schroeder-Bernstein theorem? Yeah, there are bijections between them. Does there exist one? That's not a bijection, right? Because look, if you've got, you said x to xx, well, what that does is it gives you this linear manifold, right? Yep, that's right. So you've got no linear map that'll work, because no matter what you do, the image of a linear map in this direction is going to be a linear manifold of dimension 1. So you can't have any kind of linear surjection. Right. So we've established that we need some kind of continuous function that is not linear. So we are going to develop a tool real quick that'll let us do this. One thing you might note is if I, let's do this actually. Just add a new definition. So definition, a topological space is connected if, let's say a topological space X is connected if X cannot be expressed as a union of two disjoint open sets. All right, so a couple of examples. The real numbers are connected, right? Yeah, so the real numbers are connected because if I take any open set, it'd be a union of open intervals. Its complement will be closed. By definition of closed sets, and we know that the only Clopin sets in the real numbers are the whole set R and the empty set. So if we want, let's see. So suppose that we did express R as a union U union V, where U and V are both open sets in R, and U and V are disjoint, then U and V must also both be closed. And I need the sets must be non-empty. And this can't occur, right? Because in order for both of them to be non-empty, one of them needs to be missing some things from the entirety of the real numbers, so it can't and open at the same time. One that would be disconnected would be, let's see, the subset of the real numbers, which or the subspace of the real numbers, which is R minus 0, right? So we can make R disconnected by removing a point. We call that a cut point. In fact, every element of the real numbers is a cut point. Now, any two homeomorphic spaces, if I have two spaces which are homeomorphic, so you get a function f from x to y, which is a homeomorphism, so it's both bijective, continuous, and has a continuous inverse, then if lowercase x is a cut point in x, so if I remove it, then x becomes disconnected, whereas it was connected before. Then since x and y are homeomorphic, an established property of this is that f of x must be a cut point in y. And you can see this from using the alternative definition of open sets that I gave earlier, and checking using the fact that the homeomorphism is an open map. So the idea is you say, all right, if it's a cut point in X, then there's no open interval around it, right? That, like, unless we're talking about the discrete topology, when you remove that point, it breaks apart the whole space, but like there would be no neighborhood around it that you could walk through in absence of that point to get between the sections you're breaking apart. Whereas if that were not the case in the corresponding other homeomorphic space, then the homeomorphism would not be continuous, right? There wouldn't be an open map or anything. So the idea is you could just take any point in R1, say it's a cut point, and then suppose that there's a homeomorphism over here. Well, no matter where you are in R2, there's no such thing as a cut point, right? Because it can't make this space discontinuous or disconnected. I can't make it possible to be written as a disjoint union of two non-empty open sets. So these spaces are not homeomorphic. And in fact, given two vector spaces R I or Rm and Rn, they are homeomorphic if and only if M equals N. So this will be a starting point for doing things with topological manifolds because they are locally homeomorphic to Rm and Rn. Yeah, I'm not connected. Yeah, so that is a really strong result. There's another definition I want to give really quick with a fun example that I like to reference a lot. The definition of connectedness is actually hard to prove things about. So it's difficult to prove things about spaces when you need to invoke connectedness and prove whether it's connected in certain conditions or not after certain manipulations. So there is a slightly stronger condition or state on a space than connectedness, which is called path connectedness. So a topological space, actually, let's define paths first. So let X be a topological space. So TS, a continuous function. Oops. F from the subspace of the real numbers, which is a closed bounded interval from 0 to 1. We sometimes write I for this. To X is called a path in X. From f of 0 to f of 1. And we require that this be a subspace of R. Oh, is it broken? Yeah, I think it's for you because on our second device it's working correctly. Try like hopping out of it and then coming back in. And see if it helps at all. If not, I can try reconnecting. Okay. Did it help? Okay. Let me try disconnecting and coming back. What about now? Oh, okay. Yeah, so I just gave a definition of a path, right? So if X is any topological space, you take a continuous function from the closed interval from 0 to 1 to X. And as long as that function is continuous, it's called a path in X from f of 0 to f of 1. What you're used to thinking of is not quite exactly this. Like a path is not quite exactly what you're used to thinking of as paths. If I drew a space X and I drew this, which is, let's see, this is I from 0 to 1. and I denote the endpoints of it here like that. And then say I've got the path goes through the space like this. What is going on? All right. Maybe it crosses over itself or something. It's still continuous, though it's not picking up and moving anywhere else. This would be a path. But you're probably used to thinking of this thing itself as being a path. That's not, in fact, what a path is. A path is this part. It's the mapping. It's the function itself. It's not actually the image of the function in the space. Because that image is just a subset of the topological space. Properly, it's f of I. Right. Now, in order to be continuous, in general, we have to use the subspace topology on I, which is the open sets in I are the unions of open intervals. And because this is a subspace, you actually have closed on one end being still open, as long as the other endpoint of that interval is open. Yeah, so you just look at how you take an open set in the space, say something like an open circle here, and you check how it maps back over to this domain of the path, which would be something like that, right? And if no matter what open set you choose in the codomain, you get an open set in the domain, then this path is continuous. So this is what a path looks like. Now, second definition, a space is path connected if for all pairs of points A and B in X, so the space X is path connected if for all pairs A, B, and X, there exists a path F from I to X with F of 0 equals A and F of 1 equals B. So this would be an example of a path connected space because I can take any 2 points, no matter where they are in this space, and connect them by some kind of path. Now, if I were to take the subspace of R2, which is obtained by having 2 circles, this would not be path connected because I could pick a point here and a point here, and there would be no path through the space which connects them, right? No continuous function. This is a consequence of the topology, the subspace topology on this space. It is possible to construct kind of pathological counterexamples. But yeah, this is a much easier condition to prove. And the nice thing is, I'm not going to prove this right now. This would be a good exercise if you wanted to try it, but X is path connected implies that X is connected. So if you want to prove a space is connected, sorry. Oh yeah. So for that, I'll show you an example in just a second. It's possible to get really strange pathological, pardon the pun, behavior with path connected spaces or non-path connected spaces. And there's also a really interesting space called the Sierpinski space, which is let X be this, just 2 points, and let the topology on X be this. Empty set A and AB. This is a path connected space, it turns out. Yeah. So if I were to illustrate this, it's just 2 points, right? It's A and B. What are you laughing at? Oh yeah, the professor status thing. Funny. Yeah, so the open sets, I'll now draw them. These are not open sets that I can just walk around in, right? All I can do is I'm confined to these 2 points. These are the space. There's nothing between. It's not some kind of continuum or anything. But here's another open set in the space, and that's all I get. And I get the empty set. Those are the open sets. This is a path-connected space, even though it consists only of 2 points, which seem to be disconnected. So you can have rather pathological examples. Yeah. So path connected is you can take any 2 points in the space and find a path that brings you from one to the other. So it doesn't matter what's in the middle. I can just set f of 0 equals a. Well, no, that's not quite right. It's explicitly constructed to be this way. It does matter what's in the middle for the purposes of establishing that the function is continuous. The path is continuous. The reason it works is because the topology is really strange. So if we want to construct a path between the 2 elements of the Sierpinski space, what you can do is you can define, let's draw it out real quick so we have a visual of what's going on. Firstly, we want, let's see, f of 0. So f is going to be from I to AB, right? And I want f of 0 to equal A and f of 1 to equal B. It doesn't matter which order I pick this to be in, or which one I chose to put the open set around, because I can always reverse a path and I still get a path. Like if I let the path go in the opposite direction, it's still a path, no matter what. So in this case, I'm actually going to, let's see. I think the way you can do this is f of x, or f of t conventionally, because you think of it as going along time, right? You walk along a path in time, equals a if 0 is strictly less than t is strictly less than 1. So along the interior of the path, you have a. So let's check that this works. So we can actually draw this here. So call this axis t and call this x. And let this be b and let this be a. And now our path is going to look like this. It's going to be closed here, and then let's let this be 0 and this 1. And then this will be open, and this will be closed. Right. Okay. Now, the open sets here are both A and B. So if I take both of those, I get the whole space, which is open by definition of topology. Like I get this whole thing, right? Which is I. I don't have to check for B. It would be disastrous if I had to, because if I plug in B for F inverse, right, I would just get literally just the single point 1, which is not open because it's a singleton, like it's a closed interval in some sense. It has to do with being the real numbers being Hausdorff space is why that's the case, but I won't go there right now. singleton sets are not open in the real numbers. Well, actually, you know this because we've said that any open set contains an open neighborhood of its members. So what I have to check is if I plug in A, do I get an open set along the time axis? And it turns out that I do, because this, everything except for this point, this is a closed set, so the complement of it is open. It's open. So this is in fact a path. So the space is path connected. And the way it looks, if I were to do it in time, I just stay at A for the entire duration of the path, except at the very last instant at which I jump to B. So that's the first of the two pathologies that I want to show you. The second one is what's called the topologist's sine curve. So our question is, does connected imply path connected? We know the converse is true. Let's see. So I don't have to think of F inverse of B because I only consider yes, that's right. Yep. Yeah, the Sierpinski space is specifically defined so as to exhibit this pathological behavior. That's right. So the second pathological case is we have a question. It is, does connected imply path connected? And we'll see that it doesn't. So the way we do this is, let's work with a subspace of the real numbers. Or sorry, R2. So let's define a space as U. And U is going to be the set, let's see, 0, T, where -1 is less equal to T, less equal to 1. So this is just a vertical line. If I'm looking at R2, I've got this, and then U looks like this. And then V will let be T sine of 1/T, where T runs from 0 open. Where do we want to let this end? Let's see. Should I do pi over 2? I'm just going to do pi, I guess. Yeah, that'll work. And then we'll let it go actually over to, you know what? No. Make that part open. The pi 1/2 pi. Okay. So what this looks like is this. This will be V, and it will be open, so it won't contain this endpoint over here, but it will go like this. And it never actually touches the red line. So U and V are disjoint. Now, moreover, I could actually delete these two, and I would get that U is open and V is also open. They're not open in R2, but in the subspace topology that X, which is defined as U union V, the subspace topology on this space X, U and V are both open. Because if I take, let's see, if I take the square which contains V, it does not contain U because it lies on the boundary of that square, then V is the intersection of V with an open set in R2. So V must be open by the definition of subspace topology. And then U, let's see. U is not open. Is that right? That's right, that's right. So we didn't actually need to delete these parts. Okay, that's good. For some reason, I was thinking this would be a disconnected space, but no, it's connected. Because anytime I take an open circle around a point in U, it has to intersect with V. So every point of U is a limit point of V, I should say. So the space is connected, because I can't write it as a union of two separate open, disjoint, non-empty sets in X. So X is connected. But my question is if I let lowercase u be an element of U and V be an element of V as points, is there a path F from I to X with F of 0 equals U and F of 1 equal to V? And you just need a picture to figure this out, really. So can I get a path that goes from the red part to the blue part? Remember that the path needs to be explicitly constructed. As in, you need to actually be able to draw such a path. They never touch, but recall that every point of U is a limit point of V, so U and V get arbitrarily close. Like, it seems like you should be able to walk from U over this really dense region and then start tracking along the curve, right? Or maybe you could like start up here and kind of, I don't know, like do something like that and asymptotically hop on to the blue part in some sense. I mean, I know that doesn't make any sense properly, but like intuition seems to suggest that there should be a path between these two spaces that are infinitely or infinitesimally close to each other infinitely often, especially since we're just working on a plane. So yeah, it turns out that there's no way, right? Because you would need to actually figure out what each point needs to be along the path. The way you would prove this is you suppose there is a path, and then you show that you get some kind of contradiction with the continuity of it. Yeah, particularly at the first location at which you're not on the red part anymore, like the first time at which you're not on the red part anymore, you show that continuity breaks there. So you can show that this space is not path connected. So connected does not imply path connected. All right, so that's cut points in homeomorphism. That's homeomorphisms, path connected, connected. A bit of terminology real quick so you can read Munkers a little easier if you decide to go on from this. X, being a topological space, can have certain characteristics called separability. So I'm going to draw out a space, 2 points in the space, in fact. Let this be A, let the other one be B, and they're both elements of X, topological space. So X is said to be T0 separable if for every pair of points I can get some open set around each of them that doesn't contain the other. I think that's actually Fréchet separable. You should just be able to do it in one direction for, yeah. Like the Sierpinski space, this would be T0. T1 separable would be called Fréchet separable. If for any 2 points I can find open sets around each point that separate them. A counterexample to T0 is the space with 2 points, which just has the open set and the whole set as open sets. So this, you can't differentiate between these points with open sets. T2 separable spaces are called Hausdorff, and this is probably the more important, certainly the more important separability criterion. So Hausdorff. Hausdorff was the creator of the current definition for what a topology is, I believe. So A and B must be separable by disjoint open intervals, or open sets. Then there are normal spaces. So if I can take any closed set in the space and any other point, and I can separate them in the same vein as I'm able to do with Hausdorff criterion, then the space is called normal, if I can do this for every pair of things in this fashion. And the space is called regular if I have the following condition, almost like normality. I can take any 2 closed intervals, or closed sets, sorry, and I can separate them with disjoint open sets that contain them. So normality and regularity are useful for 2 theorems called Urysohn's lemma and the Tietze extension theorem. These are extremely useful in analysis, real analysis. We will not cover those. They're in Munkers, about roughly halfway through, I think. But Hausdorff has a nice condition. So the idea with Hausdorff is let X be a point in X. Note that for any Y in X, Y not equal to X, so any separate point Y, there exists neighborhoods, one around X and one around Y, such that U of X and U of Y are disjoint. Now, the trick is take the union over all those UYs. So if I pick out another point, then I can get an open set around this one, an open set around this one. Well, just let Y be all the other points. So you get a union for all Y in X, Y not equal to X, of the open set around Y that you get from this Hausdorff criterion. Take the unions of all those. And what you get is a superset of the set Y in X such that X is not equal to Y, which is equal, this may be equal, to the set X minus X. And when you do this, you can then take the complement of this set, and so the complement, I'm not going to write that part on the bottom again, but that's what's there. The complement of this is precisely equal to the set, the singleton set X. And because this is an open set, because it's an arbitrary union, it's a union of open sets, when we take its complement, we get a closed set. So in Hausdorff spaces, all the singleton sets are closed sets. Yes, you guessed it. Good. That's right. So Hausdorff, an important criterion or consequence of Hausdorff criterion is that singleton sets are closed. And the way you do it is just to like kind of take all the other points, union together intervals or set open sets around them, and you're done. Now, I think you should be able to do this with Furché spaces, right? Because the argument doesn't change if these two overlap. As long as X is not in the open set around the other one, you should be good, I think. You just need this open set around Y. One around X is not sufficient. It would be if you could take arbitrary intersections, but we can't do that. So you can only take finite intersections. No. Those are the separability criteria. There are actually a lot more than this. And the naming scheme for them is really erratic and hard to memorize, but these are the important ones. Now, here comes the fun part. So all this was just building up to this point. We're going to start building up geometric spaces, or things that you usually think of as being geometric. Right. So part 2. I'm actually going to take like a 2-minute break, and then we'll come back. All right, 1 sec. All right. I thought I had put it right here. Yeah, that's precisely it. So what, let's see, let me look at the, yeah. Yes, so it turns out the Sierpinski space is path connected, and therefore also connected, right? But I need you to check something for me. How is it connected? No, it's not discrete. Let me give another definition real quick. So there's two topologies we get on any set, right? So of course, recall what the criteria were for a topology. We had 4, right? So there's 2 initial ones, which are the topology has to contain the empty set as an element, as an open set. And it also has to contain the whole set as an open set. So if I let a topology on a space X be equal to the empty set and the whole set, well, now we have to check the other 2 criteria for this one. Well, it's easy. We just need to check if it's closed with respect to unions. Well, the only unions we can form are the ones that have X in them and those that don't. And any that has X in it is going to be X after taking the union. And if it doesn't, then it's going to be the empty set. And so it's closed with respect to union. And intersections, pairwise intersections, you're good there too, because if it contains the empty set, then it's empty. Otherwise, it isn't. It's X. So this is called indiscrete, the indiscrete topology on X. And that's what I'm saying is IN discrete. And then there's another topology, which is precisely the power set on X. And this is called the discrete topology on X. Yeah, so closed, let's go back up to the definition. So what I'm saying is for closure under pairwise intersection, I realize there's like an overlap in terminology here. This is standard. So don't let that make you think I'm talking about closed sets, right? Closed means an algebraic idea that if I take 2 open sets and I take an intersection of them, I'm still in the topology. So when I say closed, I mean I can't leave the topology by taking the intersection of 2 sets. But closure actually turns out to be something else too in topology. So we just have to keep in mind that we're working in topology or that we're working with the algebraic operations that we can do in topologies. Yep. So these 2 topologies are naturally available everywhere on every set. The Sierpinski space is not discrete because in order to be discrete, it should look like this, right? But we're missing that open set around B. The discrete pair like this is not a path-connected space. But I actually claimed something erroneous earlier, that path-connected implies connected. But as you can see, if we check this, actually, no, that wasn't erroneous at all. Is the Sierpinski space connected? We know it's path connected, I've already checked. But we need to check if it's connected. We know the path connected implies connected, but are you sure that I was right about that? So the only open sets available are X, A itself, and the empty set. And well, there's no way to write X as a union of 2 disjoint, non-empty open sets. So we're good. It's it is connected. Good. Right on. Yes, that's right. The circles denote open sets. The space itself is just intrinsically the points that you see. The open sets are just illustration. You can't actually walk around in the open set. You can only walk around on the points individually. You can only be present at a point if you're something living within the space, per se. Like sometimes people speak of ants that live on the surface of a sphere. Well, the sphere is a set, and on the sphere, here's the equator, loosely, and we could draw open sets on this, that this sphere inherits from as being a subspace of R3, with the open sets in R3 being the open balls of varying radii. And you can see that an open ball would intersect here to give me like an open circle on the face of the sphere. Right, so here we can walk around within the open set because every point that I'm drawing there inside that little dotted circle is a point on the sphere. But in the Sierpinski space, those open sets are just containers for dots. You can't actually walk around within those containers unless you're on the dots. Okay, so two ideas you'll need here for the second part. You should keep in your mind the idea of a path, right? So we define paths as being continuous maps from I to any topological space, where I is just the closed bounded interval 0 to 1. And then just recall that this needs to be continuous. And you will need to know a little bit about groups, like how to take quotient groups. Paths you'll need for homotopy, and we're going to do a little simplicial homology, which will require that you know a little bit of algebra. Both of them will, actually. Okay. So before we do all that, let's define a couple of new ways for constructing spaces, topological spaces. And I can review groups if you need. By the way, that's not going to be an impediment. Just let me know if you feel uncomfortable with any terminology I use there. Or haven't seen something. So yeah, so let F be a continuous surjection between two topological spaces. So it's onto. Now, we get the equivalence relation from F. We'll call it tilde. You could write sub F if you wanted, but I won't. The meaning will be clear when I use it. And this is an equivalence relation on elements of Y. So we say that Y is equivalent, or Y1 is equivalent to Y2 if, sorry, it's going to be an equivalence relation on X, my bad. X1 is equivalent to X2 if f of X1 equals f of X2. Now, you actually get the same thing even without the surjection. Like, you get this equivalence relation anyway. But we'll need it for something we're going to construct in a second. We'll need surjectivity. What we say now is class X1 equals class X2 if x1 is related to x2 by this, or if they're both sent to the same element of y. Set definition of equivalent. Yes, that's right. Transitive, symmetric, and reflexive. You get a partition on x by this. Yep, that's right. And in fact, it turns out that y is precisely identifiable, or is actually a partition of x. We do require surjectivity for that, because if it had some elements that couldn't be reached by mapping from x to y via f, then we would not be able to say that y is a partition of x. It would be a superset of a partition. Now, let's see. See if I can find a better charger. This one doesn't seem like it's going fast enough. You will not need separability now. That was just an addendum in case you wanted to. I can't. This doesn't go to USB. Yeah, that was just to give you a primer if you wanted to go on to. Oh, nice. Let's do that then. Thank you. That was to give you a primer in case you want to go on to the main analysis related theorems of Muncrist. Yeah, that doesn't work at all. It doesn't even say it's charging. All right. So regarding partitions, it is possible that y is all of x. Yes, that's right. If it's a bijection, then you just get the same thing back. Right. Y is x precisely if it's a bijection. Did it say it worked over here? I don't know. I'm trying to think if that implies they're homeomorphic, but I don't think it does. It just says there's a bijective continuous map between them. You may be able to get like really pathological cases where there's a continuous bijection that has no continuous inverse, and you won't be able to construct one. I'm not sure about that. It may. Bijection is continuous. We won't need that either way. So what I write is f, and we'll do an example of this. So x mod is how I'll read this, tilde, or x mod f is equivalent to y. We'll say is y, defined as y. And in order to do this, let's see. And Y is actually, we can change Y not to be a topological space, but any set A. And so we say, given the topology such that f of u being open in, or sorry, u being open in X implies f of u is open in A. Okay. Right, so this, we say that A is a quotient space of X. And F is then a quotient map. Okay, so an example of this. Start with the square as a subspace of R2, right? And then, yeah, so basically the idea here is you don't really need to think about this notation. It's kind of ugly. But think about whatever, that you've got this. X is a topological space. A is a set. And so you got a topology on X, and you want to import that over to A. So the way you do it is you take all the open sets in X, and you just send them through F and see what you get in A, and make those be the open sets in A. It turns out that this gives you a topology on A. It's trivial to prove this. You can do it as an exercise. But yeah. So an example that's really easy and kind of fun is you can start with this as a subspace of R2. Well, what are the open sets then? Well, it's anything interior, and also it's the unions of anything interior. And then also you've got anything that lies on the boundary and contains it, but is open otherwise. Or you could even have something that's like this, and then it's got like this part's closed, and then this part's open beside it. Like that would be open in the space. And what you can do is you can say, all right, well, let's construct a function, a continuous search action, f from, let's call this space X. So can take it from X to A. I won't define what A is yet, but make it so that F is by the way, F is automatically continuous when you use this topology. It's actually a it's not a homeomorphism. It's an open map, and it's continuous, but it won't necessarily be a bijection. So what we call it is an identification. So basically, it's an homeomorphism where you take out injectivity, and what you get is called an identification. So I'll write that for a note. Homeomorphism minus injectivity equals identification. Is the inverse also continuous necessarily? Recall that you won't necessarily have an inverse, right? Because you don't have an injection. But what you're asking is really, it's a good thing to ask, because when I say F is continuous, well, we know F is, in general, for a map, I'm not saying for this one, if F is a continuous map between topological spaces, then that means that U being an open set in the topology on Y implies F inverse of U. This is always defined, right? You can always take it in this fashion. You can always map back through sets. Is open in topology on X. So F inverse is always going to be defined this way, as long as F is continuous. Otherwise, what you get, if you don't have continuity, the codomain is just the power set of X. You always have this, no matter what conditions you have on F. You don't even need surjectivity or anything. So, but what you said is F inverse continuous? Well, recall that in homeomorphism, we had F inverse needs to be continuous. So if that's the case, then the inverse of it should be a map from the topology on X to the topology on Y. Instead of, you don't want it to just be a map for the topology on X to the power set on Y. You want it to be specifically to the topology on Y in order for this to be, the inverse to be continuous. If this is the case, then that means that F itself, if F is bijective, F is an open map. And you really don't even need this to be the case. If you let F be a function on subsets, then the restriction, it's called an open map when the inverse is continuous. So it just sends open sets to open sets. So identifications are open maps, which are also continuous and surjective, but they may not be injective. They're one-to-one. Right. Okay. So back to the example. The reason we call it an identification is this. I just have to satisfy, I don't need to know anything about the structure of a totally abstract set. Nothing, I know nothing about it other than there's a surjection to it from X. And I'm defining this to be, all right, well, this is a subspace of R2, so I can just designate points of the space X as pairs of real numbers, right? Just coordinates, like usual. So what I want is F of XY equals F of X prime Y prime if and only if X Y equals X prime Y prime. So this would be a bijection, right? Because this would be injective. Things in X would only map to the same thing in A if they are the same thing in X. But then you could also go and allow one more identification of elements of X, and that's X equal, absolute value of X equals absolute value of X prime equals 1, and Y equals Y prime. So what does this mean in the picture? Well, I didn't specify what the boundaries are in terms of coordinates, but we'll say this is -1, this is 1, this is -1, this is 1 on the y-axis. So everything maps uniquely to a point of A, except the sides here. This maps to the same place that does. just maps to the same place that that does. So the sides are getting mapped to the same place. So paths in the space can now look like, for instance, they can start here, say, and walk over here and go through the identified point and come out over here. And then they can keep going and they loop back over, right? So if I were to visualize this space, the way I'd probably think of doing it by this space, I mean A, I'd probably do it as a cylinder, right? Because I've taken these two sides and I've glued them together. And the seam is given by this. And if I were to, I could have done it in different ways, but I'm going to draw arrows here to show the way the seam goes. Huh? It's what? What about the top and bottom? Yeah, so those are separate still, right? I can't walk through the top and get to the bottom. Right. I've just identified the left and right sides. So that's actually why I drew 2 here. And, well, that was supposed to be 2 there, and then 3 here, and 3 here, because I don't want to identify those, but I drew 1 arrow here to denote that they were getting glued together. That's fine. So what's confusing about it? The fact that I've been able to draw this cylinder and say that A is precisely the cylinder. I can see how you drew it after defining identification, but I'm not sure I get what that word means. Oh, okay, okay. So identifications, recall, are precisely homeomorphisms without injectivity. So you take what a homeomorphism must be, remove the one-to-one criterion, and then you've got what identifications are. So recall, we can check that this is an identification. And sometimes when I say 2 points get identified, I'm speaking rather loosely. I'm saying they're in the same equivalence class given by this function f, which maps from x to a. So really, the cylinder is a partition of a square. Let's see, right, so what you did here is have f be a function mapping the left. Yes, that's right. So more precisely, I can draw it explicitly, right? So take this being x over to here being a, being the cylinder with a seam in it. So this point here would map over something like to here. Meanwhile, this point would map over to this point. In some sense, I've taken this space. I want to use a different color. I've taken the space and glued together the edges. What might be, yeah. The top and bottom, so, all right, so we can draw how it works, right? So the way I define the function here is, I actually didn't define it. I just stated what the identifications were, which is sufficient because you can draw anything homeomorphic to a cylinder, and A would be represented by that thing. So yeah, this point maps to here, basically. Well, more like this point, really. But this right here maps to the bottom on the backside, on the border. Yeah. Yep. Doesn't the first one go against it? Well, it's not quite injective, right? So it's saying that 2 points on the cylinder are equal, like the images of 2 points on the square are the same on the cylinder if they're the same on the square. Or there's another condition in which they might be equivalent on the cylinder, which is when they lie on opposing left or right sides of the square, where the square gets glued together to produce the cylinder. Does that make sense? There's a mapping on the top. No, that's empty. That's empty. You could poke your finger through this thin thing. Yeah. I see what you mean now. You're asking if there are caps. There's no cap, no. It's hollow all the way through. It's just this flat sheet that's been pinched together, glued together at the edges. Right. Let's see. But if we consider two different points on the opposite sides, which are mapped to the same point, then doesn't the first one tell us that they're actually equal? Let's see. No. So let me give a. So the coordinates on X may look like, as a subspace of R2, may look like this, right? XY, where -1 less equal X and Y less equal 1. Now in cylindrical coordinates on the cylinder, I can give, let's do theta and height, where theta is a real number and height is between -1 and 1. So f can actually be given as a function from xy to this cylindrical coordinate system, which is given as, well, the theta part's a little hard, so we need to think about that. So let's see. Pi and negative pi, does that work? So pi x and then y. Yes, that's right. Brandon, that's correct. Where it says curl up the long side. Wait, no, what? Yeah, curl up the long side, that one. That's what we've done. Yeah, so here you can see that this point maps to the back here. So this is about the origin, right, in R2. And it's a coordinate system for the cylinder. And we can actually draw the seam where we're doing the gluing on the other side, right? Then 0, 0 would be on our side here. I walk this way, and that takes me out in this direction. I walk this way, goes around in this direction. Strad, does that make sense? I feel like you're a little hung up on this definition I gave, and it's really just a notational thing. This is not really the crux of what's going on. The crux is the geometric picture. What I want to build up to is what the open sets. Yeah, that's plenty. We don't have to be explicit. I'm trying to stay very visual here because we're going to work with nice spaces that have expected properties. You will at times need parameterizations and need to construct these things explicitly, like these maps, but especially when doing proofs. But for the conceptual understanding, to be able to get to where you can see where to start a proof, you don't need these constructions. You don't need to see explicitly what the maps are. You just need a pictorial idea. Now, my question is, what become the, let's see. The open sets on the cylinder. And I think I told you something wrong. Yeah. So the topology is not given by importing over the open sets. It's given by, it's the minimal or the coarsest topology, or the smallest topology, such that F is continuous. Okay. Okay. So that's right. I'm doing something slightly wrong here. That can't be it. I'm concerned about the seam. The criterion for this is a little strange, right? So it's not the minimal topology. That was a good comment. Let's see if we can figure it out. So we've got to, I'm concerned about what happens when I take an open set like this, which contains the boundary here, because on the cylinder, that will look something like this. Which I don't want, right? I want the splotches with no boundary to be the open sets. I don't want it to depend on the scene. So what should we do? Right, we don't want it to. Let me see if InLab works on here. Yeah, it does. Okay. Yeah. Subsets U of Y. Oh, okay. I see. Right. So we don't have to worry about that because yeah, so we put a topology on A such that U being a subset of A is open if and only if the inverse of F maps U to an open set in X. Wait, that's wrong. Slightly wrong. Let's make this V in A is open in A if and only if U is open in X for all U in X such that F of U equals V. Is that right? I think that does it. Very technical. The geometric picture is really simple. So what we do is we say, okay, well, is this open in A, in the cylinder? Well, consider that there's a subset of the square X having this in it, which is not open. And then also having this part over here. Well, this is not open, but it maps over here to this, so this can't be open. Yeah, so that works. Rather technical definition. we can deal with that. So this is not open. Okay. Good. Now, let's look at a couple of spaces we can build up as quotients. I'm going to define a new algorithm for constructing quotient spaces. Call this a fundamental polygon. I can take any kind of polygon, and I can label vertices on the boundary of the polygon. So take a circle, for instance, or something like a circle, homeomorphic to a circle, we'll say, and contains the interior, right? So it's not just the boundary of the circle. But let's label these edges. What is going on? Okay. Label the edges. A, have this one go that direction. Have this one go this direction. So that's A. And I can actually denote this by A inverse. Because what I do is I start at any vertex I want. I walk along the edges. And if the arrow agrees with the direction I'm going in, I put A. And I keep going all the way around until I get back to the original vertex. And if it disagrees, I put A inverse. So this is specified that way. All right. I could have also written A inverse A. It would have been the same thing. Because what happens is this, since they both have one arrow on each of them, and because they both have the same letter, I'm going to identify these two edges. And so this point gets identified with this one because of the way the arrows are facing. This point gets identified with this one. This gets identified with that, and so on. Supposing along this line of reflection. And we glue these two edges up like a taco. And we get a sphere. S2 the sphere. So that is like that. Now I can make a cylinder, like I said, by doing, let's see, so this is going to be that way. Those two should get glued together. Call that A. Call that A. Make this one B. This is redundant info. I don't have to label each of the edges and also put multiple arrows. I'm just doing it because you can do either one. But the way this would be specified in terms of an edge labeling would be A, B, A inverse, and then B inverse. So I walk around in this direction if I want to. I can go the other way if I want. This would be a cylinder. This is equivalent to what I'll show you as a product space in just a moment. I cross, let's see, was it I cross S1, the circle, the product of an interval and a circle, or a cylinder, same thing. Another one would be to, and actually I did something horribly incorrect. This is not what I want. I want C. Right. So these two should not get identified. B and C should not. Now we can go a step further beyond the cylinder, and I can take these two, glue them together. Take these two and glue them together. And we do it procedurally. So my edge labeling is A, B inverse, A inverse, B. And this is going to be equal to a torus. And the way to see this is, well, firstly, you glue together the A edges. You get the seam. And then you've got B going in this direction. and you just let's see, not sure if the word is embedding. Originally we have some 2D space, but if we were constructing a cylinder, it would require some. No. These are abstract. We're not working inside of anything. There's no ambient space we're fitting in. These are purely specified by the identifications that we put restrictions on. These images are looking at a concretization of some abstract object. You can construct things that you can't draw, and I'll show you one in just a second. Things that don't live in any kind of Euclidean space at all. So this, the way we look at this is now I'm going to take the edges and bend them over towards each other. And to do that, I get this kind of macaroni noodle shape. And if you think kind of hard about it, what I've done is I've taken the back side and flipped it, so it's going to change orientation. And this one also. And then since they're both facing the same way, this point gets glued to that point, and they both just kind of link up. And they get a torus. And the open sets are exactly what you're expecting. They'd be the little open splotches on the surface, and the unions thereof. This is also a Hausdorff space, and so on. It inherits all the separability criteria, or conditions, status from its space it's being identified from. That's happenstance. I don't think that's necessarily generally the case, though. Pretty sure it's not. These are not all open sets, but these are topological spaces that I've constructed. So recall that R2 is a topological space, and the open sets are the open circles in that space. Right, so in the plane. Well, as a subspace, the square is a topological space, and its open sets are the open circles inside, and the unions thereof, so you can make any kind of open shape that doesn't contain its boundary, and also anything that contains the boundary of the square, but is open otherwise, is an open set, right? So when we take these identifications, these open sets get imported over onto these identified spaces, subject to some criteria, the quotient topology construction criteria. So some additional examples we can construct. There's one really crazy one. So this one has a rather nice edge labeling. It's just AA. And these edge labelings actually are incredibly powerful. We'll see in just a minute. When we define what homotopy is, you'll see. This is AA. What you do is you glue together this point, antipodal points. You glue together this point and this point, but you don't glue together anything else. Just what I'm saying is everything antipodal, right? So you go all the way across and see the reflected point on the other edge, and you identify those 2 points for every point on the edge. But the interior of the circle you leave unchanged. So there's one big result I want to build up to on these edge labelings, the fundamental polygons and surfaces. But this is called real projective space, or real projective plane. You cannot visualize this. You could if you let it cross over itself and keep mindful of how it works. The idea is you take it and set it up on its edge or on its vertex. You glue together the sides. You have this as the interior. And so, let's see. Is that right? These 2 points get sent to each other, the vertices. I think the way you can visualize this is like as a cross cap. So the idea is you have this bulbous thing on the bottom, and then you have like you can trace figure eights along the surface. There's a path in that fashion, I would say. Yeah, you can't really visualize this. Now, there's a really interesting thing. I posted a picture that proves this recently. That you can actually think of me drawing 2 circles, right? One example space further first. If I take the cylinder, instead of doing 2 edges reversed, I just did 1. Then what you get is you start out with a square. You have these 2 identified, and then you turn that one, and then identify this one, but backwards from the way you do it in the cylinder, because otherwise you do the top and the bottom in the same direction. You get not a cylinder, but a torus. You have this, but then you've got these facing backwards from each other, unlike in the torus example. And then you can just kind of like do what you did with the macaroni shape thing in the torus, but just for the top, right? And so this top flips while the bottom says it has been through itself. Well, you don't even need to do that just yet, but you can make the bottom swell up into this kind of gooseneck thing, and then you've still got the bottom here, and its orientation is just as it was. You didn't really do anything, you just swelled up this part of the candy cane shape. And then, furthermore, you take the same shape, you've still got this orientation on the top, on the gooseneck, and you take this part and you walk it up and you keep its orientation the same. Yep, it is. And then finally, you let this part, the gooseneck, pass through the bottom, and you connect it because the orientations are facing the same way. And I'll just loosely, vaguely draw it. So that's what you get. And you can talk about the open systems that it inherits as a quotient space of the square, or of R2. In fact, you can do linear algebra on this, in some sense. I think Nick was talking about somebody posting some kind of paper on doing quantum mechanics on a Klein bottle. That's kind of funny. But what's really interesting about this is that it's homeomorphic to this space. So each of these is the circles are going to have their edges identified so as to produce the real projected plane independently. Yes, by the way, when we talk about homotopy, we can start discussing knots. Yeah, that's what I'm trying to build up to right now. But I'm not terribly interested in knots, but there are nice algebraic objects we can construct. Remember at the beginning of the talk, I was speaking about gadgets you could produce, functors. Turns out you can take things in the category of topological spaces and build functors that let you move from topological spaces and continuous maps between them and import them over to abelian groups and just groups in general and rings and so on. And they are homeomorphism invariant. So any two homeomorphic spaces will have the same functorial representation after you map them over to this other category. Yeah, so you can do classification of different spaces based on the functorial representations of them, functorial images of them. So you can take a torus, for example, and compute some group that is invariant under homeomorphism of the torus. And then you can classify things as being not homeomorphic to a torus just by computing this functor. Instead of having to prove that there exists no homeomorphism explicitly, you can just say, okay, well, this functor differs in image for the torus in this other space. But this space here is actually two real projective planes. So I've glued together the edges and typical points on these circles. And then what I've done is I've taken a circle out of each of them in their interior and then like removed it completely so there's no hole in each of them, and then connected them via a tube, which is a cylinder. And what this is called is RP2, so that's this one by itself, connected sum. So I write a hashtag there, RP2. So this is the connected sum of two real projective planes. And this is actually homeomorphic to a Klein bottle. It's rather difficult to see how this is the case, but I posted a proof of it on Twitter. You can look at how it works. So let's see. Yeah, it was the one with the two circles, and they were really annuli, so they were like rings, and then it broke them down into rectangles, and then repieced the rectangles together again, and constructed the fundamental polygon for a Klein bottle, which was this. And it did it in a way such that it implies a homeomorphism. Yeah, your proofs no longer need to be written. You just draw pictures, essentially. Yep. So there's a wonderful, wonderful theorem, and I'm not going to prove it here. I actually don't know that I could prove it here if I wanted to. But it says that, crap, I need one more definition. So it turns out that outside of nice spaces, like the real numbers, closed sets behave in rather unexpected ways. They don't look like what you usually think of closed sets or closed intervals being. The things that we speak about closed sets being relevant for in the real numbers are not available in other spaces. It turns out you need a different construction. So one thing that we know about closed spaces or closed subsets of the real numbers, is in particular for closed bounded intervals, A to B, any infinite subset of this space must contain a limit point. Can you think of why that must be the case? So if I draw some kind of closed interval here, I can't, pigeonhole principle, I can't put infinitely many points along this region such that there's no like cluster location, like where they cluster up with infinitely many in a neighborhood at some point. I've got to pick at least one place for there to be infinitely many points in any neighborhood of that place, no matter how small the neighborhood is. I've got to pick one. So what this is called is this closed interval has the limit point compactness condition or quality. So that's limit point compactness. So X is limit point compactness, or is limit point compact if X for any infinite subset of X, E of X, E has a limit point in X. Okay. That's limit point compactness. Now closed sets have this condition in the real number line. If you're familiar with metric spaces, the notion that we've taken R in like real vector spaces and put topologies on them by these open balls that we've been using as a basis, that is actually called the metric topology given by the Euclidean metric. So what you do is you fix a positive number and you take any center for a ball, and then everything in that ball forms an open set, like that ball forms an open set, and you just let this radius range over all the possible positive numbers. You get all the open balls, which form the open sets in the metric topology. So we say that if we throw away that metric, this topological space, which is the real numbers under the usual topology, is called metrizable. So it's compatible with some metric. That means some metric could generate the topology that we do have on the space, even in the absence of this metric. There may not be just one that generates it, but we do have compatibility with some metric. So let's see. Yeah, so metrizable spaces, limit point compactness is enough for us to speak about when talking about like closed sets in the way I'm about to want to. So compactness is used in the sense, like the word compact is used to indicate something being small in some sense, because it's rather obvious that large sets don't have this quality, right? If they're unbounded, they may not contain certain limit points, or an open set won't contain limit points for any infinite subset. So if I took 0 to 1, like if I approach 0, it doesn't matter. Like I could take the set 1 over n for n in the natural numbers, and I would never, this doesn't have a limit point, right? Because 0 is the only limit point of it, and it's not contained in the open interval. So this is not a limit point compact set. So if we throw away metrizability, we need a shittier condition called compactness, which says the space X is compact if any open cover of X admits a finite subcover. All right. So open covers in general can be infinite, right? They can have countably or uncountably infinitely many members. But a compact set you can throw away. You can take any open cover, throw away all but finitely many elements of the cover, and you still can achieve another open cover. This definition sucks badly. It's very similar to the situation between connectedness and path connectedness, and path connectedness is a stronger condition under certain criteria, though it's always true for path connectedness. And it's much easier to prove things about or with. So we'll just deal with limit point compactness. Yeah, sure. One second. Yeah, so an open cover is, I was talking about this with the subbasis earlier. So if you've got a set X, or a topological space X, really, any set, then an open cover of X is a collection of open sets in X, or open sets. Yeah, I'll say the X needs to be a space, just to simplify my definition a little bit. And then it needs to be open sets in X such that we'll say U sub alpha for alpha in some index set J, such that the union over all these sets, these open sets, is precisely equal to X. That's an open cover. So basically, you can think of it this way. Taking set X and then take open sets in it. This is not an open cover. I can make some more open sets on it. Still not an open cover. You know, I can cover the whole thing, really. It's really just covering it, right? And it may take infinitely many sets to do this. Maybe not, but that's that. So the question is, why are open intervals not compact, right? Because you should be able to cover them with a single open set. Well, that's not exactly what compactness says. It says, given any open cover, I should be able to, let's see, 0 to 1. Given any open cover, I should be able to reduce it to a finite subcover. So an example why this is not compact is you can take an open cover given by this. So it's 1 over n, 2 n in the natural numbers. This is clearly a cover, right? And it's an open cover because all the elements are open intervals, open sets. But there is no finite subcover. You can't take out all but finitely many of the elements of this open cover and get another open cover. Good. Cool. But I shouldn't delete that. But yeah, we're not going to work with compactness. We're going to work with limit point compactness. Turns out limit point compactness was the original notion that people thought of. And it was only because it didn't work properly when you throw away metrizability that we needed to come up with something called compactness. No. In metrizable spaces, yes. Yep. So I have some. I think it's Heine-Borel theorem. Let's see. I think this is right. This says, and there's a proof of this in Axler's measure theory book. The compact subsets, and because R is metrizable under the usual topology, the compact subsets of R are precisely the finite unions, so unions of finitely many of closed bounded intervals. This is absolutely central in real analysis. In fact, our professor would get angry when students wouldn't remember this. And it was a daily thing that they would forget for some reason. That's Heine-Borel. Closed bounded means compact in the real numbers. And in fact, I could throw away this finite unions. Yep, that's right. Moreover, if f is continuous, and I swear I'm building up to something cool. We're almost done with these little trivial details, these little knickknacks that we need to know. So f is continuous. A compact implies f of A is also compact. So continuous images of compact sets are also compact. And the way to prove this is, you should prove this after this, after we get done. This is really essential, like fundamental, just like straightforward. So yeah, compact, yeah, for general spaces. Yep. If you want to work with compact sets, this is the theorem to prove about them. To start, it's very simple. It's a great exercise in writing down your definitions, working with things you don't quite have a good geometric intuition for, and abstractly working, proving something. Good. Very good. Let's see, what's next? Yeah, so I want to cover product spaces, and then we'll start doing homotopy and homology. So a product space, let X and Y be topological spaces. We can define a product space, XY. That's Cartesian product. I know you know what that means. So the topology on this space. Right. So since we've got a product, Cartesian product, I can write a little commutative diagram, right? or just a diagram in general. And tell me if this makes sense to you. All right, so that's my little diagram there. So the idea is that pi1 is a projection, right? It's a surjection. I'm going to call it a projection. And the idea is this. xy in the product maps by pi1 to just x. And xy maps by pi2 to just y. It should be clear why this is a surjection. Yep. Okay. Now, we do require the x and y be non-empty, because that definition does not work otherwise. It won't be a surjection. Yeah, so the topology is we can write out any subset of xy as u x v. Is that right? No, we cannot do that. We absolutely cannot do that. A subset u of x cross y is open in this topology, or this topological space, if and only if pi1 of u and pi2 of u are both open. This is going to be useful for when you do topological vector spaces, for continuing your linear algebra in Banach spaces. So the product of open sets is open. Yeah, but an open set in the product space has to project onto open sets. Is that right? It seems like it could be wrong. Yeah, just any two topological spaces. I think this is not quite right. Because this would allow me to do something like R cross R having a topology different from R2's topology, wherein I have something like an open square, right? But then I can like have this part taken out. and then make this part closed. And the way to check that this, under my definition, is not open, is open, is to look at, and I don't want that, is to project down onto the coordinate axes, and you'll see that it forms two open intervals, one separately each. So I think what you need to do is, we'll just do it the simple way. So a basis for the topology is open sets U x v well, U cross V, given that U and V, U is open in X, V is open in Y. So the unions of these things, unions of products of open sets. And this only works for finite products. When you go up to infinite products, you have a whole heap of problems. A good third of Munkers is devoted to that problem. It turns out the obvious way to generalize to infinite product spaces is called the box topology, and it breaks all kinds of things having to do with continuous functions. All sorts of things just fall apart completely. And what you have to do instead is you have to define a product topology, the Tychonoff product topology. And this is in the section on Tychonoff's theorem. But Tychonoff's theorem says we don't ever use the box topology for anything in math. We always use the product topology, the Tychonoff product topology. And Tychonoff's theorem says that when you use Tychonoff's topology, Tychonoff's product, products of compact spaces are compact. But not in the box topology. Munkers does not have the nicest proof of this. There is another book by, I think, the daughter of Ed Witten and 3 other authors, and it's very category theory flavored, but it builds up some better language for doing this proof, and it's just much nicer. It's like obvious almost. But the Tychonoff product says you get like this this product space over some index set of X alpha for all these different topological spaces. And then for each one, you get an arrow surjecting or projecting down onto that particular space called pi alpha. And a set, let's see. You did? I may have lost connection just now. Just let me know if I did or didn't. A set is open, I think, if like it has to be the whole space for all but finitely many of these X alphas. So you have to like chip away only finitely many dimensions product space if you want an open set. Yeah, you've lost connection. Whoever it was. Me. Who was my laptop connected to? Okay. Mine too. I think it was in yours, right? Test. Okay, I'm still working. I can see because my you can look and see from my name moving. Yeah, I just can't see on my laptop. Okay. Yeah, so anyway, that's the Tychonoff product topology. It has an open set, it's built up in the same way, but for all but finitely many of the constituent spaces in the product, an open set must contain the entire space. Like you have to refine down the open sets on just finitely many of those constituent spaces or dimensions. So this becomes important when you're dealing with topological vector spaces in particular, because you can only deal with finitely many dimensions at one time, so to speak. And it works nicely with metrics and so on. But anyway, this will agree with our topology on R2, right? And R3 and R4 and so on. And in fact, infinite dimensional spaces. And the Tychonoff product also agrees on Rj, where J is in any arbitrary index set, like an uncountable set or anything. So you can even take R, or R to the cardinality of R, or anything you want, whatever. And the vectors in this space will be those that have non-zero components only in finitely many dimensions. It turns out to be basis independent and all these other nice things. So it's really good. Yeah. So that is product spaces. So now that gives me what I wanted to get to with the fundamental polygons. So I needed compact sets and I needed product spaces. So now I can give the theorem that I wanted. So any compact surface, two-dimensional space, locally homeomorphic to R2. So I can't have something that's like, like a cone or anything like that. Because this wouldn't be, there's no neighborhood of this that homeomorphs onto R2, like flattens out into a plane, right? I can't establish local coordinates there onto R2. There's no chart. Is homeomorphic either to S2, the sphere. This is the classification of surfaces theorem. It's homeomorphic either to S2, to a connected sum of tori. What that means is a handle body with n many holes in it, finitely many. So this is a connected sum. You can see by just taking the tori individually, cutting out a little patch from them on the side, and then connecting them via a tube, and then inflating that tube so that it looks like it's connected like this. Those are connected somewhat. Right? This is a homeomorphism, not the connection part, but the part where you inflate the connection tube. Homeomorphism. So every compact surface is homeomorphic to sphere, connected sum of tori, or a connected sum of real projective planes. Now this is really surprising. it turns out that the ones that are homeomorphic to real projective planes connected together are precisely the non-orientable surfaces. So if you find a surface and you know it's non-orientable and it's compact, I really should say any compact surface without boundary. What do you mean by boundary, you might ask? Well, a cylinder has a boundary, right? It's the edges on the top and bottom. Okay, we can cover what orientable is. And so let me just note that these two are orientable. Yeah. So it's an easy idea. So in a plane is orientable, though it has boundaries, so it's not really in our consideration right now. If I can look at a point on it, right, and I can draw a normal vector to it. And when you draw a normal vector, a unit normal vector, you have to pick a direction, one side to the other. Now, walk around on this plane and walk the point that you're holding there, and don't ever flip this this normal vector to the other side, right? Like, don't bring it over here. You don't want that. If you can walk along any path on the surface and your orientation doesn't change, any closed path, so you go somewhere and then you return back to where you were, if it doesn't matter which path you choose, you always end up with the same orientation when you get back, then the space is orientable. Now, what's an example of a space that isn't orientable? Well, take the Mobius strip, right? It's a classic one. And a lot of stuff in topology feels kind of like artificial or simplistic or kind of childish in a way. Like, I'm dealing with this Mobius strip, which, I mean, it's like some childish toy, it seems like. But the idea is this classification theorem lets me prove things about really complicated spaces just by thinking about this really simplistic toy. So this is a non-orientable surface because, yeah, it all is. This is at the last chapter of Munkers, I think. And orientability there are certain local global theorems in geometry that you can use determinants with, but the connection is a little difficult to see now. But yeah, this is non-orientable because I can start by pointing towards me, walk along here, it points down, here it starts to flip over, ends up on the other side, go all the way around, it's on the interior. I get back to where I was, and it's pointing the other way. It's a closed path, and it flips the orientation to the surface as non-orientable. There's no consistent orientation that walks along paths and stays the same everywhere. So let's see. Right. So if a surface without boundary is orientable, then it's homeomorphic either to a sphere or to a connected sum of tora. And if it is not orientable, then it is homeomorphic to a connected sum of real projective planes. So that's really kind of surprising. Okay, so that's the classification theorem. No. Poincare conjecture is much, much stronger or deeper. Really kind of irrelevant to this. It does concern surfaces, though. And paths and all these sorts of things. So this is A good start towards it. Now, I want to do, I don't know if I want to do homotopy or homology first. By the way, hey Jacob, I just saw you joined. We'll do homology. So I need to, we're going to work in essentially Rn, like Euclidean space. It'll be up to, it'll be finitely dimensional as far as we work with it, but we are allowing as many dimensions as we want. So say R1000 is no problem for us here. So I'm going to define simplex, a zero simplex, as being a point in Rn for some arbitrary n. Can be anything. And actually, let's do homotopy first. So we know paths already. So I'm going to define homotopy. So let X, Y be topological spaces. F is a map from X cross I, which is the interval 0 to 1 closed, to Y, a continuous map. We know how to talk about this, right? Because we know what the topology on Y is, because it's a topological space, so we are given the topology there. And then we also know what the topology on this is, because we know what the topology on I is a subspace of R, and we know what the topology on X is, because we're given that, and we know what the product topology is. It's generated by the taking the unions of the basis elements, which are the products of open sets in X and I, respectively. And to check that it's continuous, you just look at the inverse, which is F inverse from the topology on Y to the topology on X cross I, which then projects down onto X. Or, sorry. Not exactly, but this is sufficient. So we can check if this map's continuous. Is called a homotopy. Between continuous maps F0 and F1. Does that make sense? Each of these are maps from X to Y, and they're continuous. And I've written a blank there because we can plug in any X. We're just holding 0 constant, right? The location in the homotopy a long time. So a homotopy is kind of like a continuous map between continuous maps, or a path between continuous maps in the space of paths. or sorry, in the space of continuous maps. So two continuous maps F0, F1 are homotopic if there exists a homotopy Ft of x from x cross I to y with f of 0. I should really say f of x0 equals f0x, and f of x1 equals f1 of x. Yeah. So yeah, these maps are homotopic if there's a homotopy between them from one to the other. Yes, x and y are spaces in general. That's right. We're trying to we're really so being homotopic is an equivalence relation on continuous functions between two spaces. So if you fix x and you fix y as the source and destination for continuous maps, then you can speak of all those maps that you've just parameterized, like maps from x to y that are continuous. You can speak of them as being in equivalence classes corresponding to whether they're homotopic to each other or not. We're trying to achieve some kind of equivalence relation on maps, continuous functions. Without assuming anything. Like we don't want to impose any additional structure on the maps or on X or Y or anything. Yes, that's right. I should say that. That's good. Yep, good. Yeah, so it's a little weird. I'll give a couple of examples. Let's talk about maps from R to R, so endomorphisms in R. Let F0 of X, so F0 and F1 are both going to be maps R to R. Continuous, of course, is, let's do sine of X, and then F1 is X squared. Okay. Now these are homotopic, and I write that as similar to homeomorphic, but I don't write two lines, I just write one. These are homotopic. And the way to see that is there's a homotopy. f, remember x is now r cross I to r, such that f of x 0 equals sine x. F x1 is, you got what I'm letting right, x squared. And then also f is continuous. And the easiest way to do this is just to lerp between the two maps, right? So the way to do it is f x t equals 1 minus t sine x plus t x squared. Does that make sense? Because when t is 0, you have 1 of sine x and then 0 of x squared. And then when t is 1, you got 0 of sine x and then you got 1 of x squared. Clearly, this is a continuous function. It's just basic algebraic operations. There's nothing crazy. Subtraction, addition, multiplication. That's it. So this is a homotopy between the two maps. Yeah. Okay. So we've got homotopies, and you can actually like get paths through the space, so we can draw the two maps. And then the other one is this, right? So the way to see that this, or some things you can do with this homotopy are, you can fix x, hold x constant, and you see that this moves at a constant pace down to here, and 0, t equals 0, you're up here, and then 1 equals t, you're down here at the sine curve. So you get paths, each point on one graph seems to move towards the other in time, straight down or straight up in some cases. And if you, let's see, you end up with these intermediate maps, which are going to look something like that, roughly. So that would be like t equals 1/2 or something like that. Roughly, anyway. Oscillatory behavior also being parabolic. So you get a kind of path in the space of continuous functions. You can make that rigorous and start speaking about arrow categories and all this, but that'll be another day. But yeah, so that's homotopy. Now, it turns out all continuous functions from R to R are homotopic. So this is really uninteresting in this case. Yeah, that's right. Continuous maps, that's right. So it becomes interesting when you start speaking about more exotic spaces, right? Because all maps from R to R are homotopic. So there's only one equivalence class, one homotopy class of functions from R to R. Very uninteresting. More exotic spaces, things with holes in them, things with strange irregularities, fiber bundles, and so on. These will all have interesting homotopy classes. Yeah, so one interesting thing is I'm about to show you actually we can leverage homotopy to acquire equivalence classes of spaces rather than just of functions between two spaces. So this is really the interesting thing. So let's see, x and y be topological spaces. So now that you've got that, we say X is homotopic or homotopy equivalent or X, Y share homotopy type. And if you've done any programming, you may have heard of homotopy type theory. That is precisely what this is, except that's a little more exotic and throws away set theory. So X and Y are homotopy equivalent if there exist maps, continuous maps, F from X to Y and G from Y to X, such that F compose G is homotopic to the identity on, well, what does G accept as an input? Y, right? So it should be the identity on Y. And also G compose, the converse, right? G compose F is homotopic to the identity on X. Audio cut out? Oh, okay. No, it works. Did you lose it a while ago? Ooh, that's not good. Okay. All right, so yeah, the YouTube video is not going to be very good, I think. We lost probably like 80% of it in some way or another. Anyway, F is going to be, it's going to accept a real number, right? Because it's from R1 to R2. And we can really just make this anything that you would want, some kind of inclusion, but it needs to be continuous, of course. Say X is 0. Seems natural. I really could have chosen just about anything. right? I could have made it plugged x into the y component if I wanted to. I could have made it x. I just needed to be an inclusion. And that's not part by definition. It just turns out that I need to do that to establish a homotopy equivalence in this case. So now what we get is, well, what's G composed F? Well, that's going to accept elements of R1, so that's going to be X. So naturally, G composed F of X is going to be identical, not only homotopic to the identity on X. And then F composed G of XY is just going to be, of course, X0. Now the question is this homotopic to the identity? So we need to ask F composed G, is it homotopic to the identity on Y? So we need to construct some kind of homotopy. So the homotopy should be a map from, well, it's from R2 to R2, right? So it's going to be R2 cross I, so because it's a homotopy, to R2, and we need Fx0 to be F composed G, so precisely X0. I know that's a little confusing because those X0s are different things in some fashion. But F, actually, what I should be doing is, this is R2, right? So I need XY. And then at the end of the homotopy, I should have the identity function. So the way to do this is to define the homotopy in this fashion. So it's going to be X always, right? Because that's just unchanging. And then we'll have some typos and horrendous user interface. Wow, that is awful. Okay. Yep. All right, and then here we just get ty, right? Because at 1 it spits out y, and then at 0 it spits out 0. So that's our homotopy. That's clearly continuous. So we've just shown that R1 is homotopic, or homotopy equivalent to R2 by constructing a homotopy between the composition of those two continuous functions that we chose, right? So there's a lot of freedom in establishing homotopy equivalence. It's freedom at 2 steps. Firstly, the construction of F and G going between the 2 spaces, and then also in the homotopy that you construct between F composed G and the identity and G composed F and the identity. You have freedom in 2 places here. Now that's homotopy. We can do quite a lot with homotopy. So let's look at a square with a circle taken out. So this is out in space. There's nothing, you can't speak of anything out here that's shaded. We only can talk about this area labeled X. And I'm going to suggest that we put this point to be called 1. Or X naught, actually. Now, there are paths which start and end at X naught. So we call these closed paths with base points being X naught. This one would have to have an orientation, so a direction. And the paths, recall, are functions f from the interval to x and this is a topological space, recall, is a subspace of the real number line, and this is also a topological space. So we can take two paths, f0 and f1, and say if they both are based at the same place. You actually don't require that for this part, but you can discuss whether they're homotopic to one another. Paths are homotopic in some space. Now, it turns out that these two are homotopic to each other. In fact, they're both contractible in the sense, what I'm saying is you can continuously deform them to a point. So you can continuously walk them back, deform them into just a point where the path is just staying at the same point for the entire duration of the time interval that you're pathing along. You're paving. That sounds right before I said it. It turns out that with this base point, there are, yeah, that's exactly right. You got the idea. Walk around here. Yeah. Is that homotopic to the others? Right. Now, I will say that this problem is, we can, let me ask you this, is this where I go around twice, is that homotopic to the one where I only go around once? If you were to think of this as like a physical problem where you've got a rope and you're trying to deform it, and it's stretchable and shrinkable, or you could pull up the end of it at the base point, x naught, you would see that you couldn't pull that slack extra ring around in any fashion so as to get the other path right. Like you might think, oh, I can pull this piece right here down to the point and make it look like it by overlapping it's the same thing, but no, that's not the same path because you're just going twice as fast around and doing the same path twice. It's not the same path. As a function, right, it wouldn't be the same thing if we look at the construction of it mathematically, but theoretically. So it turns out those two are not homotopic paths. In fact, even if I walk around in the opposite direction one time, that's still not homotopic to the one where I walked counterclockwise. And so what you get is if I walked around this way one time and then did it again, and then I walked around clockwise, the opposite direction, and came back to the point, that is actually homotopic to the one where I walk around counterclockwise once. And so the number of times I go around the hole in the space in a path in a particular direction, say counterclockwise, is called the winding number of a path in this space. And the, let's see, homotopy equivalent, if I can, you say they're homotopic. So homotopy equivalence is a condition on spaces, right? But homotopicity is, or homotopy really, is on the paths or on functions, continuous maps. So yeah, they're homotopic if you can continuously deform one path into the other. That's right. It's precisely correct. In fact, the deformation even has a specific mathematical definition. So the winding number uniquely determines the equivalence class of homotopic maps that a path in a space falls into, not homotopy type per se, because that is a quality of spaces, but there is equivalence classes. Maps can be homotopic to one another, and they are if and only if they have the same winding number around this hole in the space. Yeah. So the winding number of this path, if I establish the orientation as counterclockwise, is 1. On the other hand, the winding number of this path would be -1 if I went that way, right? 0 if I don't go around it at all. 2 if I loop around twice. If I loop around twice, then come back and then go touch, it's 1. If I loop around twice and then go back around twice, I could just walk the whole thing around and unravel it to the point. That would be a winding number of 0. Yep. Okay. So it's really a loose idea. This isn't too formal. We're not making a formal discussion yet. The way to make this formal is to recognize that any homotopy equivalent space to X, this container space we're dealing with, will express the same properties in terms of homotopies in that space, or of functions, paths in that space. The same characteristics will be present in the homotopy equivalent space. And it turns out that a circle is precisely homotopy equivalent to X. And you just pick a base point, X naught. Yep. No, there's no. Yeah, that's right. That's right. So you can't pass through there. You can only pass through the boundary of the circle. Your paths have to be through there. So in algebraic topology, you are dealing with, in homotopy theory anyway, you're dealing with homotopic classes and spaces. So you can always simplify to some homotopy equivalent, simpler space like this. Now, why are we doing closed paths like this? Well, you heard me speak about the equivalence classes of paths, closed paths, or loops, determined by the winding number that they have around the circle. Have you seen group theory at all? Okay. So we have a functor that takes us from a topological space to a group called the fundamental group of that space. So I'm going to say this space is S1, this one-dimensional sphere, circle. And we have this functor, which acts like a function. It eats up S1 or any topological space. In fact, if I write it properly, P1 is a functor, or you can think of it as a function, from the category of topological spaces to groups, GRP. And so what this is the group of, actually I have to specify a base point. So this is actually the pointed topological category. So given a particular base point, x naught, the fundamental group, pi 1, of S1, the circle, is the equivalence classes of paths with base point x naught that start and end at x naught in S1. Now this isn't just a set, right? It must be a group, as I've said. So what's the operation? Okay, so I am going to suggest that there's a multiplicative operation. And so take two paths. Let's deal with x first. So it's going to be the same for x and for S1. So the idea here is, let's call this a path f and this one g. Now f is a function from I to x. G is a continuous function from I to x as well. And because they are homotopic to one another, they lie in the same equivalence class, because that's how we define the equivalence classes on these paths. But in general, we can define the operation on these classes to be written by a little square. And what that is it's going to be the equivalence class of the path f squared g, which is from I to x, still continuous, such that f square g t equals g of 2t if t is less than or equal to 1/2, and f of, 2t minus 1 if t is greater than 1/2. So it's concatenation. So f composed g says we go through the one on the right side first. So you go through g at twice the speed that you went through it initially when it's just g, and then you go through f. So that looks like this. All right. So that's concatenation of paths. And that's the group operation in the fundamental group. And you get another path when you do that. So it eats up two paths, spits out a path that's longer, but takes the same amount of time to travel along. It spends half its time on the first path and the other half of its time on the second path. another example of path concatenation? Oh yeah, absolutely. Great question. So let's do this. The identity is, I want to concatenate a path to this one. Let's say F. I want to concatenate a path to this such that I stay in the same, I get a new homotopic path to it. So if I concatenate a constant path where I just stay at the base point the entire time, then it's homotopic to the original path that I'm concatenating the constant path to. Does that make sense? Because all I got to do is like shrink away that constancy via homotopy to get a homotopy between the two. So the identity in this group is precisely the constant map, or the equivalence class, or the homotopy class of the constant map. So I want to get something for an inverse for this element of this group. I need something that concatenating with this makes it homotopic to the constant map. And it turns out that if you have a path F, then its equivalence class has an inverse given by the equivalence class of the path that is, let's see, T gets mapped to 1 minus T. So it just reverses the direction. Sorry, that's a little bit wrongly stated. So it should be T gets mapped to F of 1 minus T. So really all that is just saying the inverse of this one is going that way along the exact same path. Because then all I got to do to deform this new path into the constant map is to walk this new edge on up. So I get a path that looks like that now. Yeah, that's right. Absolutely right. Always true. Yep. All right, so now we got a group. Okay. So this is the fundamental group of a space. And it turns out that since we know that the homotopy, the equivalence class of homotopic paths that a particular path lives in this space, the circle, depends fully on the winding number of that path. And the winding numbers are precisely the integers. If I have a path that starts at x0 and goes around 17 times, and then I concatenate it to another one which goes around 3 times, so this is F, this is G, and then F concatenated to G has winding number 20. And so concatenation corresponds to addition of the winding number. Now, we can actually say that this fundamental group as a group is isomorphic to the integers. Yep, it does, absolutely. Yep. Now, some rather nice theorems about this. So if I've got two spaces, X, Y, and I think they need to both be compact for this, then the fundamental group of X cross Y with base point x naught, y naught inherited from each of them. So these are pointed topological spaces. They have a base point already picked out for us. This is actually going to be it's going to be equal. I'll be careful. I'll just say isomorphic. It's going to be isomorphic to the fundamental group of x naught, Cartesian product with the fundamental group of y naught. Now this only works for finite products. So one case we can do is if you've got a torus T2, this is actually equal to S1, the circle, cross S1. And these are both compact, right? Because they're closed bounded subsets of R2. And because of that, the fundamental group of the torus with x not picked out, whatever it is isomorphic to z squared. Now, do you know what the fundamental group of the real number line is? Yeah, absolutely. You can compute the fundamental group for a lot of spaces just by geometric considerations, like pictorial reasoning. R only has winding number 0 when equivalence class, right? So winding number does not generalize to all spaces. It's just for those homotopy equivalent to the circle. But yes, you're right. All the pads, the closed pads in R are homotopic, so it's just the trivial group 0. That's right. Yeah. Now keep in mind that left out a technicality. When you're doing these homotopies, you can't move the base point during the middle of the homotopy, so it has to stay constant. But that's not really relevant. Like it doesn't change anything ever. Let's see. So the fundamental group of the sphere. Yeah, that's right. There is a generalization of this, or a stronger notion called the fundamental groupoid, which is categorical. And it removes the dependence on the base point. But you just end up with this monoidal category. It's like annoying. So what would be the fundamental group of the sphere? Yeah, that's right. Yep. And then let's see. Fundamental group of the Sierpinski space should be also trivial. Yeah. Okay. Now, if you take a, let's see, there's another operation you can do. So if one thing is, if you got two spaces x, y, and they're homotopic, or sorry, they have the same homotopy type, then they have the same fundamental group. So one thing I can do is, we've got this thing called a wedge product, and I think it's written this way. So if I've got two spaces x and y with base points x naught and y naught, then the wedge product of them is the topological space, where you have x disjoint union with y with identification x naught equals y naught. So you glue their base points together and nothing else. So for two tori, if they have base points like this, I can attach them at the base points and get T2 wedge T2, and this will have fundamental group. Z4. And also, I think you were asking about knots earlier. It may have been Brandon, but if you have a knot, you can embed it in some space, say R3, and then let it live in there, and then call the knot K. And then the fundamental group of the embedding space minus K is called the knot group of this knot. And it turns out you can actually do something kind of neat here. You can take two circles and you can ask, let's see. You can compute their knot groups, and you'll see that the one for this is the trivial group, I think. I'm pretty sure this is a trivial group. And then the one for this is z squared. And what this says is, I pick out a base point anywhere here, and then I look at all the loops going around these knots, not touching them, and think of all the homotopy, the equivalence classes of homotopic paths in the embedding space, the ambient space that contains these knots, or these circles, and I compute the fundamental group from those. And it says that I can unravel any path and contract it to a point in this space, no matter what I take. I can unknot anything. And for homotopy, there's one last thing I want to say. if you have got a complicated space and you don't know how to compute the fundamental group for it, you can break it down into constituent pieces that have some overlap, common overlap between them, and you can compute the fundamental groups of the individual pieces and also of the overlap, and then that tells you what the fundamental group of the whole space is by a theorem called, let's see. Whoa. All right. Seifert-Van Kampen theorem. SVK. That one has a nice proof in Munkers. People seem to like the proof of that one in Hatcher, but me and a couple other people find it pretty unreadable. Like the way he states the theorem is really hard to understand. So Munkers is very simple there. Yeah, that theorem took me a long time. Because I was trying to do it from Hatcher, and he sucks. So, righto. So, Munkers, I looked at that book, and after I realized the proof was in there, and it just like immediately clicked. So, much better. There's one other thing for homotopy. Forget what it is. What is it? Homotopy. Oh yeah, the fundamental polygon theorem. There is a beautiful, beautiful theorem that says if you take a fundamental polygon and you glue together its edges with some kind of identification via an edge labeling, then you can, in certain cases, compute the fundamental group of it very easily. So we're going to use this to compute the Klein-Bottle's fundamental group. All right, so let's build up the Klein-Bottle. So firstly, it's like a cylinder in this fashion, but then we take these and put them in opposite directions from the torus, label these two A and B, and then note that the edge labeling is A, B, inverse, A, B, right? Now, note that this is sending this point to this point, so they're getting sent in the gluing of B to this point, and this point at the bottom left is getting sent to the bottom right via the gluing on A, and because it's at the beginning of B, it's getting sent to this point. So all four of these vertices are getting identified with one another. Also, my Wi-Fi just died. Oh, there it is. All vertices. When this happens, when all four vertices or all of the vertices in fundamental, or sorry, in a fundamental polygon get glued together in the identification, you can immediately compute the fundamental group of the resultant space. And so the fundamental group of the space, let's go darker color, of K, the Klein bottle, it doesn't matter what base point you pick, is isomorphic to the free group on two generators. With relation A, B inverse, A, B. And that's it. That is precisely the fundamental group of the Klein bottle. You just plug the edge labeling in for your relation. So it's very easy to compute. The proof of it's really nice too. Simple proof. Won't do it though. I think it's in Munkers. Last chapter probably. It's the classification of surfaces chapter. Yeah, so what it says is it's the group where, like, AB would be the cyclic group on two generators, or not cyclic, but the free group on two generators. So what it is all the elements of this group are words in just A and B in their inverses. And to get this group, all you do is you quotient by the group generated by this, the subgroup generated by that. It's cyclic, so it's commutative, so it's normal. Or sorry, that's not. It's the kernel of some homomorphism, so it's normal. So basically, you send this to the identity of the group. All right. Now, that's roughly as simple as you can get this. There's no simpler way to represent that group. There is one more thing in fundamental group, and that is every group, no matter what, is a fundamental group of some topological space. To see this, note that any group can be written as with a presentation like this. So you just write A, B, C, so a generator, all the generators. So in fact, you can just write out all the generators, G sub alpha, or alpha in some index set, so arbitrary set of generators, with presentation being also arbitrary. Now, you just construct a fundamental polygon that sends all the vertices to the same point, and you take all these words and put them as the edge labelings, and that gives you precisely what you want. Like this theorem, the edge labeling gives you the fundamental group of the space, says that, okay, we can get this group to be the fundamental group of this surface that we're constructing. And then you're done, in essence. Let's see. Yeah, so the main point here is that we can take any topological space, or precisely any pointed topological space, and go to groups, and then prove things using algebra about the space, and in fact the homotopy type of that space, because if two spaces are homotopy equivalent, then they map to the same thing by the fundamental group functor. And then once we prove something about it in the category of groups, you can map back via this surface classification theorem, and you'll have results about topological spaces proved using tools from algebra. So you can prove things that are extremely difficult topologically. There are some actual examples of this, though I don't have a good idea of the landscape of how this is done or what's been done with it. Okay. Yep. And you can go the other way too. If you have trouble proving things about groups, then you can go to topological spaces and then backport your results to groups. What's been bugging you?
This is the world's longest topology talk.
Yeah. We did everything explicitly though. We
That's
like
awesome.
a bunch of people. Huh?
That's awesome.
Well, I was hoping it would be.
Oh shit. Damn. That's really cool. How long have you been
Let's
going?
see.
Since like 2 p.m.?
2:35 or so, yeah. 2:40ish.
Damn.
I think 2:30. Yeah. Yeah,
Nice.
so it's called Pi 1 because it's the first homotopy group. There are higher homotopy groups like Pi 2, Pi 3, Pi 4, so on. And they are they correspond to classes, like equivalence classes of homotopic paths between let's see. So you got these loop spaces in the topological spaces that you're building the fundamental groups on. And those are just these maps I into the space. I am pretty sure what happens is you just build up products of these intervals for the domains of the paths. And you consider these like homotopy classes of not paths, but like surfaces that are closed or glued around the edges to the point. And then volumes that are glued around the edges to the point, and so on. And it's just the same thing. You just consider homotopy between these blankets or like parachutes and whatever. Yeah, that has to be it because that's, I think Vygotsky was talking about that in a lecture and he said it that way. Hired, yeah, that's precisely right. Yep. In S1, these math includes hello, testing. Better? Okay. Yes, sir. So I want to show simplicial homology and then we'll end there. Right. Let's see. Okay. So we're going to work in Euclidean space, so Rn, essentially. So a zero simplex is a point. Let's see. I might denote by and zeros x and one select is x naught x1 in square brackets. And it has orientation going this way. The two simplex would require one more extra point. X naught, x1, x2. And we would denote that by x naught, x1, x2. Oh yeah. Yeah, so one simplex is this thing here. So it's basically it's this. So it's 2 points joined by, it's 2 zero simplices joined by a line, basically, with an orientation. Okay, so then a 2 simplex is a triangle in some sense. So it can just be a line, like you can have collinear points, and that's fine. And it's written this way. And the orientation is inherited from the ordering of the vertices. And so to see the orientation, you've got x naught going to x1, you've got x1 going to x2, and then you've got x naught going to x2, because it's you don't go like this. The ordering matters severely. That may be kind of unintuitive at first, but you just go in ascending order when you're deciding the orientations of the one simplices. But one thing to note is that there are many, for high n simplices, you have many different possible orientations. You can't go from a higher index to a lower one. You can. We'll see in just a second. So 3 simplices, you can imagine that they are just formed by 4 vertices. So you have a triangle at the bottom and then another point up here. You get a tetrahedron. So this is x naught, x1, x2, x3. So suppose this is x naught, x3, x2, x1. So this one will go that way, that one will go that way, this one that way, and all 3 will go up. Now, this actually forms a group. So you can take formal sums of simplices. So if you've got 2 simplices, sigma and tau, you can add them together as a formal sum. let's see. Yep. There's a formal sum. Okay. There's no equivalence classes. You can't say that two zero simplices are in the same equivalence class. This isn't you don't do any kind of identification before you form this group. You don't even have x naught plus x1 equals 2x naught or anything like that. It's just, this isn't a billion group. No identification to speak of. Commutative. Additive. So that's essentially all there is to say about simplices. I mean, they're pretty straightforward, like nothing complicated. Now, we do have some additional structure on, and I should say we get these groups which are, we get a sequence of groups or a chain, excuse me, a complex of groups. So denote by C sub the nth chain group. And what that is it's a group generated by the n simplices under the group operation we just defined. Okay. And you have this for all n in the natural numbers and 0. So you also have 0 simplices, or 0 chains. Now, this gives you a complex, C0, C1, C2, C3, and so on. And why did I draw arrows instead of commas? Well, there's a way to downgrade between these chain groups. So the way you downgrade is you need an additional construction first. So we need what's called faces for simplices. So let sigma n be an n simplex. So if it's an n simplex, then we can write sigma n equals x naught x1 dot 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 up through xn. We define maps, n plus 1 many maps, epsilon in I is defined to be a function from Cn to Cn minus 1 and it's given by this. So you plug in, we're going to define it on the generator for Cn. So you plug in an n simplex, and you have x0, x1, dot dot dot, xi minus 1, xi hat, xi plus 1, dot dot dot, up through xn. And that's wrong, and it shouldn't be that way. It should be just the simplex equals, and then you get the same thing, with the xi omitted. So it just takes out the ith vertex. Produces an n-1 simplex. And the way it operates on general chains, in chains, is it distributes over addition. So if you have a formal sum of some n chains and you apply the ith face map to them, then it removes the ith vertex from each of them. Now, I'm going to define a new map. So the idea here is if I apply, let's say this is x naught, x1, x2, the two simplex. This is x naught, x2, x1. Right. Then the ith face map, or the 1th face map, this is going to be x0, x2. So it just takes out this and returns everything opposite. So it's the face opposite x1. So it gives me this. Now, I'm going to define this operator called the boundary operator on n-chains. Some people write like sub 3 here, like del sub 3. I won't do that because I prefer this notation and it works better when you start doing homological algebra. So we'll just leave it as it is. And this is defined on this entire complex, the map, every n-chain group down to the n-1 chains. It's neither an injection nor a surjection in general. The way it's defined is if you've got an n simplex, then the way it's defined is you take the sum from I equals 0 to n of, -1 to the I of the, let's see, I should specify rather that the group of all the n simplices is written this way, del n. Not group, but the set of all n simplices is written this way. And this spits out the ith face map iterated over all the vertices. Of the simplex. Bless you. Now, when you go up to singular homology instead of simplicial homology, these two things will swap places. But right now, this is properly the way it should be. And this just distributes linearly over formal sums of n chains in the, or n simplicities in the chain group. Yeah, these in the singular homology definition, you'll actually see this way. It'll be a composition of maps where this is just a continuous map, because these will be continuous maps from this to some space. So you can actually define homology on any space by changing what the simplices are. They're just continuous maps from like simplices embedded in Rn into X. That's really the only difference you have. But for now, for simplicial homology, things are a little bit simpler to think about. So you usually just do it here, and then it's a natural thing to move over to singular homology, which is a fully general tool, functor. Now, this is the boundary operator. So what it does is, if I take x0, x1, x2, and I apply, let's call this sigma 2, then I apply the boundary operator to sigma 2. This will give me, well, can you compute that for me? The first element is going to be maybe good if I just write step by step. Minus, right? So then what happens is I just delete those vertices, right? Last one should be plus. Yes, that's right. Very good. So that this is going to spit out x1, x2, and then minus x0, x2, plus x. And remember, this contains the interior. x0, x1. So if I draw this, well, it's going to be x1 to x2. And then you also have x0 to x2. And then you'll have x0 to x1. So you get one simplices, right? You don't have the boundary anymore, or the interior, excuse me. You just have the boundary. Now, an important part of this is, well, firstly, note that when you do this for a one simplex, you get 2 zero simplices. And this is why Stokes' theorem is defined the way it is. Actually, Stokes' theorem is kind of almost exactly this, the generalized Stokes theorem. Yeah. No, so like not back itself. So the group of -1 chains is not actually a group. Let's see. Well, it's a trivial group. Yeah. Being a vacuous sum, right? So 0 essentially. No simplices added in themselves. So the boundary of any point is nothing. Right, yeah. C negative n is just the trivial group. That's right. So then, let's see. A couple things to note about the boundary operator. If you apply it twice, this is just the zero map as a group homomorphism. They're all group homomorphisms, though. Yeah, so that's that. Now, because these are group homomorphisms, we can talk about their kernels and images and so on, co-kernels and all that stuff. Now, we need this chain complex. So I'm going to suggest that we define two new groups, or name two new groups that already exist. Definition of CN. Yeah, so it's CN is actually, oh, I have better language to describe it now. It's the group generated by sums of n simplices, or generated by the n simplices. Just formal sums of them. Yep. All right, now I'm going to define Z n for all n in the integers to be equal to the kernel of del, the boundary operator. Let's see. Is that right? Kernel. And what I said earlier about this right here, del, applying this twice, giving 0, is the boundary of a boundary is nothing, right? So no matter what I take the boundary of, if I take the boundary of a boundary, I don't get anything. So let's see. So let's ask, we've got two groups, cur-del intersected with Cn, and we've got image del intersected with Cn. Now, I need to figure out which one's a superset of the other in general. So the idea is I apply the knowledge that del squared equals 0. And I ask, well, I know that everything in the image of del is in its kernel, right? Because if I send something through del once and I send it the second time and get 0, then the image is a subset of the kernel. So we have this relation. And also we say that this sequence is an exact sequence. So chain complexes form exact sequences. It's right. No, I wrote it backwards. I see what you're saying. Yep. You're right. Good. Now, yeah, okay. So I want Z to be the bigger one. An exact sequence is it's any sequence where I have like a bunch of arrows which are functions. And for any two consecutive functions in the sequence, I should be able to say that the image of F is equal to the kernel of G. This is not true, by the way, because it's not an equality, right? It's just complex, not an exact sequence. Right. So we don't have exactness. You're right. Good. But it is a complex. So we require that to call some sequence like this a complex. This subset criterion. We can name all these del's, these partial, or the boundary maps, something else entirely. Like we could call them all separate things, and we would get. And properly, I should be saying that this is a restriction to C1, this is a restriction to C2, and all this. So they're different maps, but whatever, that's fine. Now that we've got this relationship, I wanted this to happen because of something I'm about to do. So the kernel of del intersected with Cn is Zn, and this is called n cycles, the group of n cycles. And Bn is the image of the boundary operator intersected with Cn, and this is called n boundaries. Now, the idea is cycles in general are things that look like boundaries of some simplex, but they may not contain an interior always. Or, for example, you might have one that does contain some parts of an interior. It would just be a cycle, it wouldn't be a boundary. These things manually. Like everything we're doing is totally computable. So now I'm going to form a third group, or really a fourth group here. And for all let H sub n, capital N, be equal to Z in mod, what is it, B in. Okay. Hn is the nth homology group. And we've been speaking about these simplices living in Rj, that infinite dimensional space, that's Euclidean space. But you can let them live in space. And then we Hn, we define Hn on a space X, where the simplices live inside X. They are this is the nth simplicial. And I should write a little triangle here to denote simplicial. Homology group of X. Sometimes people just say it's the nth simplicial homology of X. So let's compute this for a couple of spaces. One thing I will say, there's something called the homotopy axiom for homology, and it says that if two spaces, X and Y, are homotopy equivalent, then all of their homology groups are the same. So that will give us some additional help in computing these homology groups. So for the real numbers, let's compute let's the homology for point. So what the homology mean? So what of what is H0? So I want to figure out what this is isomorphic to. First thing we do, yeah. Sure. It turns out that was me. I don't know why it keeps resetting like that. Yep. So did you catch the part about the homotopy axiom? So if two spaces are homotopy equivalent, then they have the same homology for all n. So let's compute the homology of a point. Okay. So this, to do this, firstly we need to compute all the chains, right? So what is the zeroth chain group for a point? So C0. Yeah, that's maybe using my script for homology. Oh, it's really okay. Seems like it's working. Yeah, a lot better. Okay, really smooth. Good. Okay, so for, yeah, I might be writing my superscripts and subscripts wrong for the homology, because there's also cohomology, and you invert the superscript and subscript for the H groups, but it's inconsequential. I mean, when you read about it formally, you'll see what it is supposed to be. Yeah, so for the point, we can compute the simplest homology, which is you start with a chain group, right? So the zeroth chain group, what is that? So that's going to be the group generated by the O subscript. So it's going to be just Z times the like multiples of that point, right? All right. Try again. Huh. Maybe it's good. Maybe not. We'll see. It doesn't seem like it's good. Okay, it's good now. Yeah, so the zero chain group on the point is just multiples of the point. So it's isomorphic to the integers as an additive group. So we've got the first chain, the zeroth chain group. Now the kernel of the boundary operator is, well, it's exactly the chain group, because any point gets sent by del to nothing, right? It gets eradicated. This is always the case. And boundary is boundary group for zero simplices or zero chains. Oh, this is bad. It like worked just for a few seconds. Disconnected and reconnected like 10 times. It's just like works for 10 seconds and it goes out. I don't know. I thought it was on yours. Oh, switch. No, I'm on yours. No, it says I'm on yours. Okay. Let's try this again. Is it laggy? Looks laggy. Maybe not. Okay. Yeah, so all the points, all the multiples of the points get sent to nothing. They get eradicated by the boundary operator. And now we need to figure out what the boundaries are. The zero. So we ask so it's the simplices. So really x, I'll do AB such that del AB equals, actually no, it's going to be n, okay, x naught, such that there exists a one simplex AB such that del AB is it working now? Looks like it is. Okay. Equals, well, we know what this is already, right? It's going to be B minus A. But this needs to be equal to x naught, or rather k x naught. Now we know that this set is vacuous, like it's empty, right? Because you can't have this being equal to that. That doesn't make any sense for a one simplex. Unless k is 0. And that just generates 0. So then we have the zeroth homology. So that's going to be z naught x over b naught x, which is equal to c naught over 0, which is equal, isomorphic, I should say, to c naught. And c naught, we know, is isomorphic to the integers. So that's the zeroth homology of a point. Now, because a point is homotopy equivalent to r, r2, or squared, r3, r4, so on, we know now that the zeroth homology of all these is z. In fact, any contractible space, any space that you can continually deform to a point, is going to have z for its zeroth homology. So that's a rather nice fact. So we can equate the zeroth homology of z, or say that the homotopy type of a point has zeroth homology Z. Yeah. Okay. So a circle is not contractible, right? There's an idea called deformation retraction. We just say that the space isn't homotopy equivalent to a point. So there's no two maps, F from S1 to a point, and G from a point to S1 such that F of G is homotopic to the identity on the point, and G of F is homotopic to the identity on S1. Basically, anything that has holes or is not contractible. There's more things that don't have holes, and let's see, are there? There's notions of higher dimensional holes and things that lower dimensional holes that we're measuring in a homology. Now, there's a very easy intuitive for homology. One, you want to add the one cycles, not. Oh, okay. Yeah. Okay, now it seems to work. Yeah, so we want to find out what the first homology is. Now, we want to ask what the one cycle, or yeah, the one cycles in a point are. So those are the things that look like boundaries of triangles. But there may be no actual triangle that they are the boundary of. Bless you. Well, it turns out there is no such thing because, let's see. How can we argue that? I think we need to add the criterion that the simplices not be singular in the sense that a one simplex must be formed, an n simplex must be formed from n plus one many disjoint or separate vertices in the space. So there are no one simplices in the space whatsoever. So it's precisely the trivial group. And in fact, any Hn is equal to the trivial group if n is greater than 0. So we've got the entire homology complex. Or not complex, but we've computed the homology for a point. So it's 0, and then H1 x really this is isomorphic to the integers, and then Hn of x is isomorphic to the trivial group, or is the trivial group, if n is greater than 0. That should be 0. Yep. So we've got the simplicial homology for that. So this works for R, Rn, any contractible space it works for. Let's see. Second space to work with. I want to cover. It says and then there's some knowledge we have about of these. I'm out again, aren't I? I think I lost it again. Test. Okay. All right. So nth homotopy group, where n equals 1 is the fundamental group, and all the homology groups. Fundamental group is in general an element of groups. But higher homotopy groups are abelian. They're in the category E if n is greater than 1. Whereas all of the homology groups abelian. And there's a nice relation between the fundamental and homology group. So if you take you look at all of the let's see. You look at all of very angry. Yeah. Okay. Hopefully it's visible again. Doesn't seem like it. Wow. What is going on? It seems like the anger. Right. And it's off. Yeah, I see black. Completely just a black screen. The picture every 10 seconds for about a fifth of a second. You just take the fundamental group and you do quotienting by this subgroup, which is generated by all pairs that don't commute with each other and has relation I haven't written this exactly right, but you get the idea of what I'm trying. It has when you quotient, right? You take all the pairs and you an abelian group has pairs generators. The center of the group. I'm doing that. And then quotient. So you get an abelianization of the phone number. This is firstly the first home group. Wick's theorem. Joseph Rotman has a good proof in his algebraic topology textbook. Let's see. No, there's only one algebraic geometry textbook, but this is for topology, right? So algebraic topology. Rotman's text is not on the list. There's like 3, I think. There's Munkris covers it at the end a little bit. Then there's J.P. May has a book on it, and then there's Botten too, which also covers it. So there's at least 3 that go over it in good detail, and then there's a lot that use it in physics textbooks. But let's see. They essentially follow up on each other. So Munkris is the start, and then May is comprehensive. Bot 2 gives you some specialist exposition that's really nice on like cohomology, particularly de Rham cohomology. Yeah, so for simplicial homology, you can compute a bunch of different things. So we know, let's get the first homology for the circle, or actually let's just compute all the homology for the circle. So for H0 of S1, in general, for path-connected spaces, you're going to have this is equal to the 0th chain group on S1. Is that right? No, that's not right. This is going to be equal to Z. All right. Now, the first homology is going to be an abelianization of the fundamental group of S1. And we recall the fundamental group corresponded to the winding number, right? The elements of the fundamental group corresponded to the winding number of loops in the circle. And so if you abelianize that, well, Z is already abelian, so you get Z there. And then the higher homology groups are all trivial because the circle is essentially like devoid of surfaces and volumes and so on. So what this tells you really is there's one 0-dimensional hole in some sense in the circle and also in the point. So the path components actually form zero-dimensional holes in spaces. So if I've got two separate points, then in the Hausdorff usual, like the discrete topology, these will both be connected components. In fact, path components, because the space is not path connected, and the zeroth homology is going to be Z2. So you say the cardinality or the power of the nth homology is the number of n-dimensional holes in the space. So there are two zero-dimensional holes in the space. And then for the circle, there is one one-dimensional hole in the space and zero higher dimensional holes. If you were to take a wedge product or a wedge sum of two circles, so S1 wedge S1, you would get that there are two one-dimensional holes. And I'm not sure if I can like draw, let me think. If you took a volume and then you removed some surface, like a hollow hull of a sphere, and left the interior of it there. No, you should remove a volume. This should have, I believe, H2 being isomorphic to Z. And then H1 would just be the trivial group. That's it for simplicial homology. The idea is that you can just compute the homology for a homotopy type, and then you know it for all the other members of that homotopy type. So it's really quite general. There's other homology theories, though, that you can build up, and they're all similarly, hopefully similarly computable, but it tells you a lot of data about the structures that you're dealing with. This, I don't think Munkers even covers this. Yeah, homology doesn't get covered in that textbook, but he does cover the fundamental group and so on, like the homotopy stuff. Yeah. All right then. It's good to hear. Yeah, so I would suggest there were 2 or 3 different little problems I mentioned as exercises. I'll walk back through my notes and post those, and you can try proving them if you want. And also looking at that Twitter post I made with the claim that the what was it? The Klein bottle is homeomorphic to connected sum of 2 real projective planes. Figuring out how that works would be good. But yeah, that's basic algebraic topology. You can pretty much skip Munkers now. Like, we just covered all of Hatcher's notes to prepare you for algebraic topology, so you could literally just start that subject now if you wanted. Because you totally get all the computations perfectly. That was really surprising, because it took me like a month to get to where, 1 or 2 months, I think, to get to where you got today. So it's very good. Very, very good. All right. Well, we're going to hop off. I'll still be on text though, but we're gonna quit recording here. So. Open that drink already. Okay. All right. See ya.